The world does not end in a single flash. It ends in layers. First the forests thin, then the rivers run strangely, then the air itself seems to turn hostile. Across the immense supercontinent of Pangaea, heat gathers over the interior until whole regions become furnaces of dust and exposed stone. Far to the north, in what will one day be Siberia, the crust has opened on a scale almost beyond imagination. Lava floods across the land again and again, not for a day or a season, but in repeated pulses. The eruptions pour carbon dioxide and sulfur gases into the atmosphere, while metals such as mercury enter the global system and leave faint chemical signatures in rocks that will survive for hundreds of millions of years. The planet is not merely burning, its chemistry is being rewritten. By the time the Permian period reaches its final crisis, life on Earth has already endured a long succession of environmental shocks. The disaster commonly called the Great Dying is often imagined as a single apocalyptic moment, but the evidence points towards something more prolonged and uneven. Different regions fail at different times. Some terrestrial ecosystems begin to unravel before the most severe losses in the sea. In other places, especially in parts of the ancient tropics, the land crisis appears to lag behind the marine extinction. There is no single global clock striking midnight everywhere at once. Instead, the biosphere collapses like a vast structure whose supports give way in sequence. The oceans suffer most visibly in the fossil record. Warming water holds less oxygen, while disrupted circulation allows vast low-oxygen zones to spread. Nutrients wash from damaged landscapes into the sea, feeding blooms and altering marine food webs. In some places, the water may become more acidic. In others, heat and nutrient stress appear to be the more immediate killers. Scholars still debate exactly how ocean acidification varied from basin to basin, and the evidence does not support the simple picture of every sea becoming uniformly corrosive, but the larger pattern is unmistakable. Marine environments are pushed beyond the limits that many organisms can tolerate. Reef communities vanish. Entire lineages disappear. Shell-building animals decline. Food webs lose both diversity and stability. On land, the violence is quieter, but no less profound. Sulfur released by volcanism can return as acid rain, damaging soils, plants, lakes, and river systems. Mercury settles into sediments. Ozone stress may weaken vegetation. Extreme heat expands across low latitudes, while the center of Pangaea grows increasingly dry and seasonal. Forests retreat from some regions, leaving bare ground vulnerable to erosion. Without roots to hold it, soil moves more easily into waterways. Rivers change their behavior. Floodplains become unstable. The landscape begins to look stripped, raw, and unfinished. Before we go deeper, take a moment to like the video and subscribe. If this is the kind of history and mystery you enjoy, what follows is not the empty planet sometimes suggested by popular retellings. Life does not disappear completely. Even at the height of the crisis, survival continues in scattered pockets, in burrows, wetlands, deeper water, higher latitudes, sheltered basins, and ecological margins where conditions remain tolerable for just long enough. Microbes persist. Fungi and decay organisms take advantage of dead plant matter. Small animals endure where larger, more specialized forms cannot. Yet survival is not the same as recovery. A world can remain biologically alive while still being ecologically broken. The scale of loss is difficult to grasp because extinction percentages conceal the texture of what has vanished. An ecosystem is not simply a list of species. It is a network of feeding, shelter, reproduction, migration, competition, and chance. When dominant plants disappear, herbivores lose food and shade. When large herbivores decline, predators lose prey. When reefs collapse, the organisms that use them as nurseries, hunting grounds, and protection also vanish. The disappearance of one structure pulls away several others. By the beginning of the Triassic, many environments are reduced to simplified communities made from a narrow selection of survivors. The planet entering this new period is therefore not reborn in any comfortable sense. It is feverish, chemically unstable, and repeatedly disturbed. Carbon continues moving through the atmosphere and ocean in abnormal pulses. Temperatures remain dangerously high. Oxygen-poor waters linger or return. Some regions experience renewed acid stress. Ecological advances can be followed by sudden reversals. A community may begin to diversify, only to be cut back by another wave of warming, anoxia, or environmental disruption. The first stage of the Triassic is less like spring after winter than like vegetation trying to return across ground that is still smoking. Even the geography amplifies the hardship. Nearly all major landmasses are joined into Pangaea, an enormous C-shaped supercontinent stretching from high northern latitudes to the far south. Its size produces vast interiors far from the moderating influence of the sea. Seasonal contrasts can be severe. Monsoonal systems move moisture around the margins, but the heart of the continent remains prone to aridity. Along the coasts lies the global ocean Pangaea, while the Tethys Sea cuts into the eastern side of the supercontinent. These waters will become laboratories of recovery, but for now many marine habitats remain depleted and unstable. The strange silence of the early Triassic is not total. It is interrupted by the footsteps of a few hardy animals, the opening and closing of bivalve shells, the movements of amphibious predators in muddy channels, and the growth of microbial structures in shallow water. Yet the richness of the late Permian world is gone. In its place are ecological vacancies so enormous that they will eventually become opportunities. The empty niches are not invitations in the gentle sense. They are dangerous spaces, available because the creatures that once occupied them have been erased. What survives in the record suggests a planet caught between death and invention. The old order has collapsed, but the new one has not yet formed. Synapsids, the broad lineage that includes the ancestors of mammals, remain present, though many of their once diverse branches are gone. Reptilian groups begin to explore new forms and lifestyles. Amphibians spread through some freshwater environments. In the sea, a few lineages begin tentative expansions. None of these developments yet amount to dominance. They are experiments conducted under pressure. The most unsettling feature of this world is how long the crisis lasts. Modern intuition expects catastrophe to be followed by recovery, as though ecosystems possess a natural desire to return to their former state. But evolution has no memory of what used to be normal. It does not rebuild the Permian. It works with whatever organisms remain, whatever mutations arise, and whatever environments continue to exist. The result will be something new, assembled slowly from survivors that were never intended to inherit the Earth. At the boundary between the Permian and the Triassic, the planet stands inside one of the deepest transitions in the history of life. The skies carry volcanic gases. The land is scarred by erosion and heat. The seas are depleted, oxygen-starved, and unstable. Yet beneath that devastation, the first outlines of another world are already beginning to appear. Not a restored world, and not yet the age of dinosaurs, but a harsh interval of trial in which life learns, once again, how to occupy a planet that has almost become uninhabitable. The first outlines of that nearly uninhabitable planet do not come from a single fossil bed or one dramatic layer of black stone. They emerge from thousands of fragments scattered across continents that no longer occupy their ancient positions. A cliff in southern China, a dry basin in South Africa, a drill core from the sea floor, or a band of red sediment in northwest China may preserve only a narrow piece of the transition. Each site records local conditions, and no site contains the entire disaster. To find the boundary between the Permian and the Triassic, geologists must assemble a planetary event from rocks that have been buried, folded, heated, eroded, and separated by the movement of tectonic plates. The formal boundary lies at approximately 251.9 million years ago. Its internationally recognized reference point is preserved near Meishan in southern China, where marine sediments accumulated in a sequence detailed enough to compare biological change with chemical disturbance. The official beginning of the Triassic is marked by the first appearance of a tiny eel-like conodont species called Hindiotus parvus. Conodonts are known largely from their microscopic tooth-like feeding elements, which are so common and widely distributed that they allow geologists to correlate rocks separated by great distances. The arrival of this particular species offers a practical marker, but it is important not to confuse the formal geological boundary with the entire extinction itself. The collapse begins before the line in some records and continues after it in others. The rock does not display a clean dividing wall between two worlds. Instead, it preserves a compressed sequence of warning signs. Fossils become less diverse. Carbon isotopes shift sharply. Sediments change character. Mercury concentrations rise. Ash beds appear between layers deposited in ancient seas. The ratio of certain sulfur isotopes records changes in the atmosphere, weathering, and volcanic emissions. Fossil pollen and spores reveal damaged vegetation on land, while the disappearance of marine organisms documents the failure of food webs offshore. Together, these signals form something like a forensic record, but one in which the crime scene has been exposed to pressure, heat, chemical alteration, and more than 250 million years of geological disturbance. Radiometric dating provides the clock. Zircon crystals trapped in volcanic ash contain uranium atoms that decay into lead at predictable rates. By measuring those isotopes, researchers can estimate when an eruption occurred and therefore date the sedimentary layers surrounding the ash. The best dates reveal that the most severe phase of marine extinction unfolded rapidly by geological standards, within a span that may have been measured in tens of thousands of years rather than millions. Yet the environmental crisis surrounding it lasted much longer. Repeated volcanic pulses, continuing greenhouse warming, oceanic oxygen loss, and disruptions to terrestrial ecosystems extended the instability far beyond the narrow interval of maximum extinction. This difference between an extinction pulse and a prolonged environmental emergency is essential. A fossil lineage may vanish from one basin before it disappears from another. A forest may collapse while a distant wetland survives. A marine community may endure the first temperature rise but fail when oxygen levels fall later. The evidence remains incomplete, especially on land, where erosion often destroys sediments instead of preserving them. Marine environments generally produce more continuous records, while terrestrial deposits can contain long gaps representing thousands or even millions of missing years. Apparent timing differences may therefore reflect real ecological variation, incomplete preservation, or some combination of both. Northwest China has supplied particularly revealing evidence. There, mercury and sulfur signals indicate repeated volcanic disturbances associated with the Siberian traps. The rocks suggest that terrestrial environments endured several pulses of stress rather than one continuous, uniform assault. Acid rain may have damaged soils and vegetation during some of these episodes, while mercury carried through the atmosphere entered rivers, lakes, and sediment. These chemical traces do not preserve the smell of sulfur or the sight of dying forests, but they reveal that the catastrophe arrived in waves. Landscapes could begin to stabilize, only to be struck again. Elsewhere, the sequence appears different. Recent work in ancient tropical deposits suggests that some terrestrial extinctions occurred after the major marine losses. This challenges the older habit of describing the Great Dying as though every ecosystem failed simultaneously. Timing depends partly on latitude, geography, elevation, rainfall, and proximity to vulnerable water systems. A high-latitude basin might respond differently from an equatorial floodplain. A coastal shelf might lose oxygen more rapidly than an open marine setting. The extinction is global in scale, but its local expressions are uneven. Carbon isotopes provide one of the most widely recognized signals. Living organisms tend to favor lighter carbon isotopes, while volcanism, methane release, organic burial, and changes in ocean productivity alter the balance between lighter and heavier forms. At the Permian-Triassic transition, a strong negative carbon isotope excursion appears in many records. It indicates that a vast quantity of isotopically light carbon entered or circulated through the atmosphere-ocean system. The Siberian eruptions themselves released enormous volumes of carbon dioxide, but the warming they caused may also have triggered additional feedbacks involving soils, sediments, methane, and marine carbon reservoirs. Scholars still debate the exact contribution of each source, yet the scale of disruption is clear. Temperature estimates come from several kinds of chemical proxies, including the oxygen isotopes preserved in conodont elements. These indicate extreme warming across the boundary and into the early Triassic. Low-latitude sea surface temperatures may at times have reached levels hostile to many complex organisms. On land, direct temperature records are more difficult to obtain, but sedimentary evidence, fossil distributions, and climate models all point toward intense heat and pronounced aridity across broad regions of Pangaea. Rocks also record the condition of the seafloor. Dark, finely laminated sediments may form where bottom waters lack enough oxygen for burrowing animals. Iron minerals and trace metals provide further clues about whether ancient waters were oxygenated, ferruginous, or rich in toxic hydrogen sulfide. These states can change over time and vary between depths or basins. There was no single early Triassic ocean chemistry. Some shallow habitats retained enough oxygen to support communities, while deeper or restricted waters became hostile. The result was a patchwork of refuges and dead zones shifting with circulation, temperature, and nutrient supply. Fossils complete the picture, though they introduce their own distortions. Hard shells and bones preserve more readily than soft bodies. Common species are easier to detect than rare ones. An organism may seem extinct simply because the environments where it lived are no longer represented in the rock record. Paleontologists therefore distinguish between the last fossil appearance of a species and the actual moment it disappeared. They also compare many sections to reduce the risk of mistaking a local absence for a global extinction. By combining radiometric dates, fossils, isotope curves, magnetic reversals, sedimentary structures, and computer models, researchers can reconstruct the opening of the Triassic with increasing precision. Yet precision does not make the story simpler. It reveals overlapping crises operating at different speeds. Volcanic eruptions occur in pulses, atmospheric carbon accumulates. Warming alters rainfall and ocean circulation. Vegetation loss accelerates erosion. Nutrients enter coastal waters. Oxygen declines. Recovery begins locally, then falters. The boundary in stone is therefore less a line than a narrow doorway through which the planet passes slowly. On one side lies the complex late Permian world. On the other lies an interval still carrying the chemistry of catastrophe. The official geological marker can be placed within a few centimeters of rock, but the transformation it represents stretches across landscapes, seas, and millions of years. Reading those layers reveals not merely when one period ended and another began, but how long a planet can remain trapped in the aftermath of its own collapse. The doorway does not open onto recovery, it opens onto recurrence, again and again. The early Triassic appears to approach stability, and again the planet slips backward. Temperatures ease in one region, then rise elsewhere. Oxygen returns to a shallow sea, then vanishes from the deeper basin below it. New communities assemble along a coastline, only to be simplified by another pulse of warming, nutrient stress, or chemical disturbance. The Great Dying has ended as a formal extinction interval, but the forces that made it possible have not yet released their grip. This is one reason the early Triassic lasts so strangely in the fossil record. After many mass extinctions, ecosystems begin rebuilding relatively quickly. Species diversify, food webs lengthen, and reefs or forests reappear. Here, the return is hesitant and repeatedly interrupted. For millions of years, much of the biosphere remains trapped in a condition of partial recovery. Life is present, sometimes abundant, and occasionally surprisingly complex. Yet the systems supporting it are fragile. They resemble temporary structures raised on unstable ground. The atmosphere carries much of that instability. Carbon dioxide released during Siberian Trap's volcanism does not vanish when the most dramatic eruptions subside. It remains within the climate system, interacting with oceans, weathering rocks, soils, and living organisms. Additional volcanic pulses may add more carbon. Damaged ecosystems store less of it. Warming can alter decomposition and release further greenhouse gases from terrestrial and marine reservoirs. These feedbacks do not require every process to operate everywhere at once. Their combined effect is enough to keep the planet hot and to prevent a simple return to Permian conditions. The carbon isotope record preserves repeated disturbances across the early Triassic. Rather than one clean excursion followed by stabilization, the curve rises and falls in a series of major swings. Each change reflects an imbalance in the movement of carbon through the atmosphere. Ocean, sediments, and biosphere. Some of these shifts may be connected to renewed volcanic emissions. Others may involve changes in marine productivity, organic burial, methane release, or the weathering of exposed landscapes. Scholars still debate the precise cause of each excursion, but their repetition reveals a planet whose basic chemical cycles remain unsettled. Heat is one of the most persistent pressures. In low-latitude seas, temperatures reach levels that exclude many organisms or place them near their physiological limits. Warm water holds less dissolved oxygen, so rising temperature makes breathing more difficult even before circulation changes or decay consumes additional oxygen. Metabolism accelerates as conditions warm, increasing the oxygen demands of many animals at the very moment less oxygen is available. This combination is especially dangerous for active or large-bodied organisms. Near the equator, some marine regions may become too hot for diverse animal communities to persist. Fossil distributions suggest a movement away from the hottest zones. leaving what has sometimes been described as a tropical gap. The pattern is not universal, and preservation complicates the evidence, but the broader implication is unsettling. The warmest parts of the ocean, normally among the most productive and diverse, can become biological barriers. Life retreats toward higher latitudes or into local refuges where temperature, circulation, or depth offers temporary relief. The land experiences its own version of this pressure. Pangaea's enormous interior is already predisposed to dryness. Under intense greenhouse conditions, rainfall patterns become more extreme and less reliable. Long droughts may be interrupted by violent seasonal floods. Bare or sparsely vegetated ground sheds water rapidly. Rivers carry large volumes of sediment into lowlands and coastal seas. The result is not simply aridity, but hydrological instability, too little water for long periods, followed by sudden destructive movement of water and sediment. These eroded nutrients feed into the marine crisis. When phosphorus and other compounds enter shallow seas, they stimulate productivity near the surface. Algae and microbes flourish, but when this organic matter dies and sinks, its decomposition consumes oxygen. In restricted basins or poorly circulated waters, the process can create broad oxygen-poor zones. If conditions worsen, bottom waters may become anoxic, eliminating most animals that live within or on the sediment. Some seas become ferruginous, containing abundant dissolved iron under low oxygen conditions. Others may develop euxinic waters rich in hydrogen sulfide, particularly where sulfate-reducing microbes thrive. Such waters are hostile to most complex life and can interfere with the recycling of nutrients. A sea can therefore contain nutrients while keeping them chemically trapped, or distributing them in ways that do not support stable food webs. The ocean may look productive at the surface while remaining nearly lifeless below. This creates one of the central contradictions of the early Triassic. Fossils from certain locations show that complicated marine communities can appear sooner than older models once assumed. Predators return, multiple feeding levels reassemble, marine reptiles begin exploring the water, yet these ecosystems are often top-heavy, geographically restricted, or short-lived. Their presence proves that evolutionary potential survives, but not that the planet has recovered. A complex food web can exist locally while remaining vulnerable to the next environmental shock. Reefs provide a particularly striking measure of what has been lost. The great reef-building systems of the Permian collapse, and for much of the early Triassic, familiar Metazoan reefs are absent. In their place, microbial structures become more prominent in some shallow environments. This is sometimes described as a return to an older style of Earth, when microbial mats and mounds played a larger role before animals transformed marine sediments. The comparison is imperfect, but it captures the sense of ecological regression. Where reefs once formed towering, biologically intricate structures, microbial communities now occupy spaces left open by extinction. Ocean acidification may have contributed to these changes, but it must be handled carefully. Carbon dioxide dissolving into seawater lowers pH and reduces the availability of carbonate ions needed by many shell-building organisms. Some evidence supports severe acidification in particular intervals or locations. Yet biological indicators from parts of the earliest Triassic do not show a uniform, globally catastrophic acidification event. At Mission, analyses suggest that heat and nutrient-related stress may explain changes in shallow marine diversity more effectively than acidification alone. No single explanation fully accounts for the global pattern. On the continents, acidity also varies with geography. Evidence from the later Smithian-Spathian crisis suggests that low-latitude basins may have experienced more prolonged or repeated acidic conditions than higher-latitude regions. Acidic waters can alter minerals, damage freshwater systems, and affect soils and vegetation. But even here, the planet does not behave as one continuous laboratory vessel. Latitude, rainfall, drainage, bedrock, and local hydrology all modify the impact. The most severe setback within the early Triassic occurs around the Smithian-Spathian boundary, roughly 2 million years after the beginning of the period. By then, life has already begun several experiments in recovery. Ammonoids diversify rapidly in the seas, terrestrial animals expand across floodplains. Then another episode of warming and carbon cycle disruption strikes. Tropical marine temperatures rise sharply, oxygen stress intensifies, several lineages decline or disappear, and ecological rebuilding is delayed again. This pattern changes the meaning of survival. Enduring the initial extinction is not enough. A lineage must also survive the unstable world that follows. Species capable of tolerating heat may still fail during drought. Those that endure low oxygen may lose their food source. A broadly distributed animal may find refuge somewhere, while a specialized species restricted to one habitat has nowhere to go. Flexibility becomes as important as strength. Yet flexibility does not guarantee long-term success. Some early Triassic survivors become extraordinarily abundant, dominating simplified communities for a time before fading as ecosystems grow more complex. Others remain rare but eventually give rise to major later groups. Evolutionary importance is not always visible in abundance. The creatures covering a floodplain today may leave no lasting dynasty, while a small and obscure population survives at the margin and changes the future. For perhaps 5 million years after the extinction, the planet continues to oscillate between possibility and relapse. Some regions recover quickly enough to challenge the image of universal desolation. Others remain severely stressed. The evidence forms a mosaic of local success within global instability. There is no single moment when Earth can be declared healed. What finally emerges from this interval is not the return of what existed before. The prolonged crisis removes that possibility. Repeated shocks erase recovering lineages, redirect migrations, and reward unexpected combinations of traits. The delay itself becomes creative. By preventing established ecosystems from reforming, instability keeps ecological space open. Life is forced to experiment under pressure, assembling communities unlike those of the Permian. The early Triassic is therefore not merely an aftermath. It is a filter operating over millions of years. Heat, anoxia, acidity, drought, nutrient imbalance, and carbon cycle disruption repeatedly test every surviving lineage. Most experiments fail. A few persist. And in the gaps between each collapse, the first durable signs of a different Earth begin to take hold. The first durable signs do not arrive as forests reclaiming continents or reefs rising from the sea floor. They arrive as persistence. A patch of vegetation survives beside a river. A microbial mound grows in shallow water. A burrowing animal emerges after the worst heat has passed. A shell opens in a basin where oxygen has briefly returned. These are not dramatic victories, but they matter because they show that the early Triassic world is never completely empty. It is fractured into refuges, and within those refuges, life begins the slow work of spreading outward. For a long time, the aftermath of the Great Dying was imagined as a nearly universal wasteland, especially on land. That picture was understandable. Fossil assemblages from many regions are impoverished, repetitive, and dominated by only a few hardy forms. Sedimentary records often show unstable rivers, heavy erosion, sparse vegetation, and simplified food webs. Yet new discoveries complicate the old image. Some basins preserve evidence that plants survived in protected pockets. Certain river systems recover more rapidly than surrounding uplands. In shallow seas, microbial structures appear to have created local habitats where small animals could shelter and feed. The devastation is global, but survival is local. One such refuge existed in the Turpanhami Basin of what is now northwestern China. Fossil plants from this region suggest that a relatively diverse flora endured through the crisis in a protected environmental pocket. The exact reasons remain uncertain. Local rainfall patterns, elevation, groundwater, basin geometry, or distance from the most severe chemical disturbances may all have played a role. Whatever the explanation, the refuge demonstrates that extinction did not erase every terrestrial plant community at once. Some landscapes retained enough ecological continuity to preserve lineages that disappeared elsewhere. These plant survivors mattered far beyond their own persistence. Vegetation stabilizes soil, slows runoff, shades the ground, and creates small climates within larger climates. Roots hold riverbanks together. Leaves return moisture to the atmosphere. Dead plant material feeds fungi, insects, and microorganisms. Even a narrow belt of surviving vegetation can support a chain of dependent organisms. Where plants remain, herbivores have something to eat. Burrowing animals find cooler soil, and waterways receive less sediment. A refuge can therefore function as more than a hiding place. It can become a seed source for future expansion. River margins were especially important. Recent evidence from low-latitude North China suggests that some riparian ecosystems recovered more rapidly than the broader terrestrial world. These were environments shaped by channels, floodplains, shallow lakes, and seasonally wet ground. Water-moderated temperature extremes and supported vegetation even when the surrounding landscape remained dry. Floods could be destructive, but they also moved seeds, nutrients, and organic matter. In a world where rainfall was unreliable, the edges of rivers became narrow corridors of opportunity. What survives in the record suggests that these corridors were not lush in the modern sense. They were patchy, unstable, and repeatedly disturbed. Yet they may have supported more complex communities within a few million years of the extinction, earlier than older models of prolonged universal collapse allowed. Recovery here did not mean a return to the old Permian forests. It meant the assembly of new communities from whatever plants and animals could tolerate the altered climate. The same pattern appears in the sea. Across some early Triassic shelves, microbial mats and mounds expanded into ecological space once occupied by animal-built reefs. At first glance, this looks like regression. Microbial structures has been common in much earlier eras, before burrowing animals and reef builders transformed shallow marine environments. Their return after the extinction reveals how severely animal ecosystems had been reduced. But these microbial mounds were not merely signs of collapse. In certain locations, they may have acted as oases. A mound changes the seafloor. It creates ridges, cavities, protected surfaces, and variations in water flow. Small animals can settle around it. Organic matter collects in sheltered spaces. Microbial communities produce food and alter the local chemistry. In an otherwise hostile shallow sea, even a modest structure can create differences in oxygen, sediment, and temperature sufficient to support life. Fossils found within and around some of the earliest Triassic mounds suggest that Metazoan animals returned sooner in these protected settings than in the surrounding environment. These marine oases remain difficult to interpret. A rich fossil pocket may represent a stable community or a brief concentration of organisms before another crisis. It may record animals that lived there or shells transported by currents. The evidence remains incomplete. Even so, the recurring association between microbial structures and surviving animal communities supports the idea that physical habitat helped recovery begin on a small scale. Among the animals taking advantage of these openings were bivalves. Their shells are common in many post-extinction deposits, sometimes forming dense accumulations across the sea floor. Certain species could tolerate disturbed sediments, fluctuating oxygen, and unstable food supplies better than many of their vanished competitors. Their abundance is often used as evidence of ecological simplification, but it also shows how opportunistic organisms can hold an ecosystem together when diversity is low. A bivalve bed may appear monotonous compared with a Permian reef, yet it still filters water, moves nutrients, produces shell material, and provides food for predators. Simple communities are not lifeless communities. They are skeletal versions of ecosystems, reduced to a few functioning parts. These parts can persist long enough for additional species to return. On land, burrowing offered another route through disaster. Soil and sediment buffer temperature, preserve moisture, and provide protection from harsh surface conditions. Burrows known from Triassic rock suggest that a range of animals used underground refuges. Some may have entered them seasonally, others lived there more permanently. Burrowing could reduce exposure to heat waves, acid rain, drought, and wildfire. It also allowed animals to survive on landscapes where surface vegetation was sparse. The advantage was not absolute. A burrow can flood, collapse, or become depleted of oxygen. Its value depends on the animal's physiology, the depth of the soil, and the local climate. Scholars still debate how important burrowing was to the survival of particular lineages. Yet the prevalence of burrowing among several successful post-extinction animals is difficult to dismiss. In a world of environmental extremes, the ground itself became shelter. Flexibility in diet was equally valuable. Specialists tied to one plant, prey type, or habitat were vulnerable when that resource disappeared. Generalists could shift between roots, stems, seeds, small animals, carrion, and whatever else remained available. This may help explain the success of temnospondyl amphibians in many freshwater systems. These were not modern frogs or salamanders, but a broad and diverse group of often large amphibious predators. Some occupied rivers and lakes, while others moved across floodplains. Their feeding strategies appear to have been flexible enough to exploit unstable communities. Water gave them access to prey and protection from surface heat, but their success was not simply a matter of being aquatic. Freshwater systems were also vulnerable to warming, acidification, drought, and sediment influx. Temnospondyl recovery therefore reflects adaptability rather than immunity. Some lineages spread widely, acting as pioneers in habitats where more specialized predators had disappeared. Microorganisms, fungi, and decay communities performed much of the hidden work. Dead vegetation, carcasses, and organic debris accumulated after the extinction. Decomposers broke this material down, recycling nutrients into soil and water. In some deposits, unusual fungal or microbial signals have been interpreted as evidence of widespread decay following vegetation collapse. The details remain debated, but there is little doubt that microbial life expanded into the spaces left by larger organisms. This unseen world mattered because recovery begins chemically before it becomes visually impressive. Nutrients must circulate, sediments must stabilize, organic matter must be processed. Microbial communities can both help and hinder that process. They may create oxygen, bind sediments, and provide food, but they can also consume oxygen and contribute to toxic conditions. Like nearly everything in the early Triassic, their role depends on location and timing. The survivors that dominate these landscapes are not necessarily the strongest or most advanced. They are the ones able to tolerate inconsistency. They reproduce under pressure, disperse across disturbed terrain, accept poor food, and endure conditions that change before adaptation can become specialized. Their success may look unimpressive in anatomical terms. Many are small, some are slow. Others possess simple feeding strategies. Yet ecological history often turns on such qualities. The empty world is therefore not conquered in a single expansion. It is stitched together from refuges. A riverbank connects to a floodplain. A plant pocket spreads along a basin margin. A microbial mound supports a small marine community. A burrowing animal survives one more season and produces another generation. Each local success becomes a point from which life can advance. Most of these experiments leave only faint traces, a layer of shells, a root impression, a cluster of spores, a filled burrow, or a mound of laminated carbonate may be all that remains. Yet together they reveal the first true architecture of recovery. Life does not wait for the planet to become safe. It occupies the least dangerous places available, and from those narrow footholds, it begins to rebuild a world that will never again resemble the one that died. From those narrow footholds, one animal spreads with such extraordinary success that it seems almost to belong to the landscape itself. Its fossils appear across vast regions of the southern supercontinent, sometimes in numbers so great that entire assemblages seem built around its presence. It is not elegant, fast, or outwardly formidable. It has a barrel-shaped body, short, powerful limbs, a blunt head, a horny beak, and 2 tusks projecting from the upper jaw. Its name is Lystrosaurus, and for a time after the Great Die-In it becomes one of the most abundant large land vertebrates on Earth. Lystrosaurus is often introduced as the creature that inherited the ruins. That description is memorable, but it can also be misleading. It did not suddenly appear after the extinction. Several species already existed during the late Permian, and most members of the wider group to which it belonged did not survive the crisis. Lystrosaurus is therefore not a newly evolved conqueror arriving in an empty world. It is a survivor from an older order, one of the few representatives of a devastated synapsid lineage that manages to cross the boundary and flourish under conditions that eliminate so many others. Synapsids are the broad evolutionary branch that will eventually produce mammals. Lystrosaurus is not a mammal and should not be imagined as a primitive version of one, but its skull and jaw belong to a lineage already distinct from reptiles in the narrower sense. It is a dicynodont, part of a once diverse group of herbivorous therapsids that range from small burrowers to animals approaching the size of modern cattle. The name dicynodont means 2 dog teeth, referring to the paired tusks that remain after most other teeth have disappeared. The rest of the mouth is dominated by a hard beak. This arrangement is well suited to cropping vegetation, but exactly what Lystrosaurus eats remains debated. It may have pulled up roots and underground stems, clipped low-growing plants, or processed tough vegetation growing close to the ground. Its broad skull and strong jaw muscles suggest powerful bites rather than delicate chewing. Food is likely swallowed after limited processing, perhaps with the help of grit or muscular digestion farther along the gut. In the stripped and unstable landscapes of the early Triassic, an ability to consume coarse, low-quality plant material would have been extremely useful. Its posture is another reminder that this is not a modern mammal in disguise. The limbs extend partly to the sides, though not in the fully sprawling arrangement seen in many reptiles. The forelimbs are heavily built, with strong bones and broad attachments for muscle. These features have often been linked to digging. Some researchers have proposed that Lystrosaurus excavated burrows or enlarged existing shelters, while others caution that sturdy forelimbs could also reflect the demands of supporting a heavy body or moving through uneven ground. Fossil burrows attributed to the animal remain uncertain, yet the possibility fits the broader pattern of post-extinction survival. Underground shelter could protect against heat, drought, and sudden environmental extremes. Lystrosaurus itself is not one uniform creature. The genus includes several species of different sizes and proportions, spread across what are now South Africa, Antarctica, India, China, and parts of Russia. During the Triassic, these regions are connected within Pangaea, or separated by distances far smaller than today's oceans suggest. The distribution of its fossils later becomes one of the classic pieces of evidence supporting continental drift. The same unusual land animal could not reasonably have crossed modern oceans, but it could move across connected ancient continents. Its great geographical range is part of the explanation for its survival. A lineage spread across multiple regions is less likely to vanish because of one local catastrophe. If drought destroys one population, others may persist in a wetter basin. If acid rain damages vegetation in one latitude, more distant habitats may remain tolerable. Yet range alone cannot explain its abundance. Many widespread Permian animals disappear. Lystrosaurus must also possess some combination of ecological flexibility, reproductive resilience, and tolerance for stress. The fossil record suggests that in some early Triassic communities, Lystrosaurus accounts for an astonishing proportion of the preserved large vertebrates. Popular accounts sometimes claim that it represents as much as 90% of land vertebrate fossils in certain formations. Such number should not be treated as a measure of the entire planet. Fossil preservation is biased, and a dense concentration in one basin may exaggerate regional dominance. Even with those cautions, its prevalence is remarkable. Few large terrestrial animals have ever become so conspicuous immediately after a mass extinction. This abundance says as much about the emptiness around it as it does about the animal itself. A healthy complex ecosystem contains many herbivores occupying different feeding zones, moving at different speeds and responding differently to seasons. A landscape dominated by one or two hardy forms may hold enormous numbers of individuals while remaining ecologically impoverished. Lystrosaurus becomes successful in a world where many competitors are gone. Large predators are reduced, and vegetation has been simplified. Its reign is therefore both a triumph of survival and a sign of how damaged terrestrial ecosystems remain. Bone growth offers clues to the pressure under which it lives. Microscopic sections show that Lystrosaurus can grow rapidly, especially during favourable intervals. Lines within the bone may record pauses linked to seasonal hardship, drought, or food shortage. Rapid growth could allow young animals to reach safer body sizes quickly, while the ability to slow development may conserve resources when conditions deteriorate. The interpretation of growth marks is not always straightforward, but the bones suggest an organism accustomed to strong seasonal variation. Its tusks also preserve a record of life. Unlike ordinary teeth replaced in sets, the tusks grow continuously from open roots. Their internal structure can retain chemical signals from diet and environment. Studies of tusk growth have even been used to investigate whether Antarctic individuals experience seasonal metabolic slowdowns resembling torpor. The evidence has encouraged comparisons with hibernation, though true hibernation cannot be demonstrated from fossil tusks alone. What can be said is that Lystrosaurus living at high southern latitudes endured long cycles of light and darkness, as well as severe seasonal change. The most intimate clue emerges from South African rock in the form of an extraordinarily rare fossil embryo preserved within what appears to have been an egg. Early therapsid reproduction is usually almost invisible in the fossil record, so the discovery offers a rare glimpse into how a distant mammalian relative began life. The embryo is curled tightly, with parts of its skull and skeleton already well developed. Its proportions suggest that it belongs to Lystrosaurus or a very closely related Dicynodont. The egg appears surprisingly large relative to the adult animal, and its shell was likely flexible or leathery rather than rigid and heavily mineralized. This does not mean Lystrosaurus reproduced exactly like a modern reptile. Reproductive biology among early synapsids was probably diverse, and one fossil cannot reveal the full range of nesting or parental behavior. Still, the embryo suggests that egg-laying remained part of the synapsid condition, long before live birth evolved in mammalian ancestors. More importantly, the young animal may have developed to a relatively advanced stage before hatching. A larger, better developed hatchling could move, feed, and withstand environmental stress sooner than a helpless one. Researchers have proposed that producing robust offspring inside large eggs may have helped Lystrosaurus survive the unstable aftermath of the extinction. That remains a hypothesis rather than a proven explanation, but it adds reproduction to the list of traits that may have favoured the genus. There is a cost to such a strategy. Large eggs demand substantial energy from the parent and may require protected nesting sites with stable temperature and moisture. Leathery shells lose water more easily than hard shells. Success would therefore depend on choosing suitable ground, perhaps within vegetation, damp soil, or sheltered hollows. The fossil does not reveal where the egg was laid or whether adults guarded it. No single discovery can reconstruct the private life of the animal, but it transforms Lystrosaurus from an ecological statistic into a living organism reproducing amid environmental crisis. For all its success, the reign is temporary. As the Triassic progresses and ecosystems become more varied, Lystrosaurus declines, new herbivores appear, predators diversify, and vegetation changes. The traits that perform well in a simplified disaster world do not guarantee permanent dominance in a recovering one. Its abundance fades, and the genus disappears while other Dicynodonts continue along different evolutionary paths. This is the paradox of Lystrosaurus. It survives the greatest extinction in the history of complex life, spreads across continents, and becomes the emblem of the early Triassic land world. Yet it does not found a dynasty that rules the Mesozoic. Its achievement is narrower and perhaps more remarkable. It occupies the interval when survival itself is the dominant ecological skill. In its beak, tusks, powerful limbs, rapidly growing bones, and rare fossil embryo, the anatomy of endurance becomes briefly visible. Then, as the ruined world grows crowded again, the animal that seemed almost impossible to replace quietly gives way. As Lystrosaurus fades from dominance, the question it leaves behind becomes larger than any single survivor. What kind of body can function on a planet of extreme heat, unstable rainfall, poor food, and recurring oxygen stress? The early Triassic does not reward one perfect design. It favours a shifting collection of traits: efficient breathing, flexible metabolism, rapid growth, small size, broad diets, seasonal dormancy, strong limbs, and the ability to escape into water or underground. None of these guarantees survival. Together, they reveal how anatomy becomes a negotiation with catastrophe. Body size is one of the first patterns paleontologists notice. After major extinctions, Fossil communities often contain smaller animals than those that came before. This is sometimes called the Lilliput effect, after the miniature inhabitants of the fictional island. Small animals require less total food, reach maturity quickly, and can shelter in spaces unavailable to giants. In hot climates, a small body may also release heat more easily because it has more surface area relative to its volume. Yet the pattern is less simple than survivors physically shrinking. Recent research suggests that the average size of a community can fall because large species disappear and are replaced by newly arriving small species. A lineage may remain roughly the same size while the ecosystem around it becomes dominated by smaller forms. In some locations, body sizes fluctuate unpredictably as climates shift and different organisms move in. The evidence remains incomplete, but the broader lesson is clear: there is no universal command telling every survivor to become small. Extinction changes which bodies are present. Small size brings disadvantages as well. A small animal loses water quickly and cannot store much energy. Its body temperature responds rapidly to environmental change. In open landscapes, it is vulnerable to predators and sudden heat. Survival, therefore, depends on behavior as much as anatomy. Activity may shift toward cooler hours. Animals may remain close to water, hide beneath vegetation, or retreat into burrows during the hottest periods. The fossil record rarely captures such routines directly, but burrow structures, bone growth, and habitat distribution suggest lives organized around avoiding extremes. The physiology of Triassic animals is much harder to reconstruct than their bones. Terms such as cold-blooded and warm-blooded are too crude to describe the likely range of strategies. Modern animals occupy a spectrum. Some reptiles can maintain elevated body temperatures through activity and behavior. Some mammals allow their metabolism and temperature to fall during torpor. Large bodies retain heat, while small bodies may warm rapidly in the sun. Triassic species probably use similarly varied combinations. Bone tissue provides one line of evidence: rapidly deposited, highly vascularized bone may indicate fast growth and an active metabolism, though it does not prove mammal-like temperature control. Growth rings can record seasonal slowing, but they can occur in both ectothermic and endothermic animals. Oxygen isotopes may preserve information about body temperature, yet the signals can be altered after burial. Scholars still debate the metabolism of many major Triassic groups because no single measurement provides a decisive answer. Therapsids inherited several features that may have supported relatively active lives. Their limbs were becoming more vertically positioned beneath the body, reducing the sideways bending associated with a fully sprawling gait. Their jaw muscles were powerful, and changes in the palate and skull may have improved feeding and breathing. Some later members of the lineage developed whisker-like sensory systems, insulating hair, and increasingly mammal-like physiology. But assigning all of these traits to early forms would go beyond the evidence. Breathing while moving is especially important in a hot, low-oxygen world. Many sprawling animals bend their bodies from side to side as they walk, which can interfere with lung ventilation. Modern lizards often alternate between bursts of movement and pauses for breathing, although some have evolved ways around this constraint. A more upright posture stabilizes the torso and can permit longer periods of sustained activity. This does not mean every upright Triassic animal is fast or warm-blooded, but posture changes the mechanical possibilities of the body. Archosaurs and their close relatives will eventually exploit these possibilities with extraordinary success. Their lineage includes crocodilians, pterosaurs, dinosaurs, and birds, along with many Triassic groups that leave no living descendants. One of their most important advantages may have been respiratory efficiency. birds possess a system of air sacs and largely one-way airflow through rigid lungs, allowing fresh air to move across gas exchange surfaces during both inhalation and exhalation. Crocodilians also show directional airflow, though their lungs and ventilation operate differently. Because both branches of living archosaurs possess forms of one-way airflow, researchers have proposed that parts of this system originated deep in archosaur ancestry. Fossil skeletons cannot preserve lungs, but vertebrae, ribs, and internal bone spaces may show where air sacs were present. Clear evidence of extensive air sacs appears later in dinosaurs and pterosaurs. For earlier archosaurs, the reconstruction is more uncertain. Even a less elaborate form of directional breathing, however, could have improved oxygen uptake during activity and helped animals cope with warm environments where oxygen demand was high. Air sacs also affect body design. They can lighten the skeleton, ventilate the lungs, and help move heat away from internal tissues. In later dinosaurs, extensions of the respiratory system invade the bones, creating hollow spaces without greatly weakening them. This arrangement is often associated with giant size, high activity, and flight, but its earlier stages may have served more modest purposes. An animal living under respiratory stress does not need to become enormous for efficient airflow to be useful. Temnospondyl amphibians follow a different solution. Many possess broad, flattened skulls, strong limbs, and bodies suited to life in rivers, lakes, or marshes. Water buffers temperature changes and supports body weight. Ambush hunting reduces the need for prolonged pursuit. Some temnospondyls may have relied partly on skin or mouth surfaces for gas exchange, as modern amphibians do, though the extent varies and cannot always be inferred securely. Their aquatic habits provide access to cooler conditions but also expose them to oxygen-poor water, drying habitats, and sudden floods. The skulls of some large temnospondyls contain sensory grooves linked to lateral line systems, allowing them to detect movement in water. This gives them an advantage in muddy rivers where vision is limited. Their wide jaws can seize fish, small tetrapods, and other prey passing close by. Such a body is not designed for speed across open ground. It is designed for patience, concealment, and efficient feeding in a narrow ecological zone that remains productive when surrounding landscapes are harsh. Other survivors invest in armor. Thick plates, osteoderms, and reinforced skulls appear in several Triassic lineages. Armor protects against predators, but it may also store minerals, support muscles, and alter heat exchange. The cost is weight. A heavily protected animal must spend more energy moving and may struggle during food shortages. As with every adaptation, success depends on context. Armor is valuable where attacks are common and vegetation remains sufficient. It becomes a burden when migration and speed matter more. Teeth reveal another kind of flexibility. Sharp, uniform teeth suit animals that seize flesh or fish without much processing. Broad crushing teeth allow shells, insects, or tough plant matter to be broken down. Beaks reduce the need to replace complex tooth rows and can crop a variety of foods. Some Triassic reptiles develop highly specialized dental systems, but generalists often dominate the earliest recovery. When food webs are unstable, a mouth capable of accepting several kinds of food may be more useful than one perfected for a resource that could disappear. Reproduction also determines which bodies persist. Rapid maturity allows populations to rebound after drought or local collapse. Large clutches spread risk, but each offspring receives fewer resources. Fewer, better developed young require greater investment but may survive difficult conditions more effectively. Eggs must tolerate heat and water loss, while nests require suitable sediment and protection, fossils rarely reveal clutch size, incubation, or parental behavior. So many reconstructions remain speculative. What survives in the record suggests that there was no single successful reproductive formula. Seasonal dormancy may have provided another escape. Modern amphibians and reptiles can enter states of reduced activity during drought or cold. Mammals and some birds use torpor to conserve energy. Growth interruptions in fossil bone and tusks hint that certain Triassic animals slowed their metabolism during unfavorable seasons. Whether this qualifies as hibernation or estivation cannot be known with certainty. Even a modest reduction in activity, however, could stretch limited fat reserves and reduce exposure to heat. The most successful bodies are therefore not necessarily those that perform best under ideal conditions. They are those that continue functioning when ideals vanish. A powerful predator that requires abundant prey may lose to a slower animal capable of eating almost anything. A giant herbivore may be replaced by smaller forms that mature faster. An aquatic hunter may flourish while rivers persist, then disappear when channels dry. A burrower may endure the heat only to be overwhelmed by flooding. The Triassic body is a compromise written under pressure. Limbs move inward beneath the torso. Lungs become more efficient in some lineages. Growth accelerates or pauses with the season. Beaks, tusks, armor, sensory canals, and broad jaws solve different pieces of the same problem. Life is not adapting to one stable new world. It is adapting to instability itself. These experiments remain scattered and incomplete, but they establish possibilities that will shape the rest of the Mesozoic. More upright posture opens the way to sustained movement. Improved breathing supports greater activity. Rapid growth shortens the vulnerable early stages of life. Flexible diets allow expansion into disturbed habitats. Some of these traits belong to lineages that will vanish before the Triassic ends. Others will be inherited, modified, and pushed far beyond their original function. For now, they are simply ways of staying alive while the planet continues to test the limits of flesh, bone, and breath. While bodies on land are learning to survive heat, drought, and unstable seasons, another experiment is beginning beneath the surface of the Triassic seas. At first, the water does not look like a place from which a new world could emerge. Many shelves remain oxygen poor. Reef systems are shattered. Seafloor communities are simplified, and vast stretches of deeper water may still be chemically hostile. Yet the ocean is never uniformly dead. Currents shift. Oxygen returns to some shallow habitats. Microbial structures rise above the sediment. Shell beds spread across disturbed seafloors. Within these temporary windows, marine life begins assembling new food webs from the remains of the old. The first communities are often dominated by organisms capable of enduring fluctuation. Bivalves become particularly conspicuous. Some species spread across enormous regions, forming dense concentrations where more diverse permeant assemblages once lived. Their success reflects both resilience and opportunity. Many can filter suspended food directly from the water, tolerate sediment disturbance, and reproduce rapidly when conditions improve. They do not require a mature reef or a complex habitat. A flat sea floor with sufficient oxygen and passing organic particles may be enough. Dense shell beds can give the impression that recovery is advancing quickly. Thousands of individuals may occupy a single layer, but abundance is not the same as ecological richness. A community dominated by one or two opportunistic species resembles an emergency system running with only its essential parts. It processes food and creates biomass, yet it lacks the redundancy that makes complex ecosystems stable. If one dominant species fails, there may be little ready to replace it. The shells themselves reveal changing environmental pressures. Thin forms require less material to build and may grow quickly, while thicker shells offer greater protection but demand more energy and carbonate. In warm, chemically unstable water, shell construction can become costly. Some lineages reduce ornamentation or remain small. Others flourish where local chemistry is more favourable. Scholars still debate how strongly ocean acidification shaped these patterns because heat, oxygen loss, nutrient stress, predation, and preservation can produce similar signals. Gastropods, brachiopods, and other benthic animals also return unevenly. Brachiopods had been major components of Paleozoic seas, but the extinction removes much of their former diversity. Bivalves increasingly occupy habitats and feeding roles once shared with them. This shift is not completed immediately, and brachiopods continue to survive throughout the Mesozoic and into the present. Still, the balance of marine life is changing. The Triassic Sea is not simply refilling empty positions with the same kinds of organisms. It is redistributing ecological importance. Above the bottom, ammonoids undertake one of the most dramatic recoveries. These shelled cephalopods are related to modern squid, octopuses, and nautiluses, though their external coiled shells make them visually distinct. The end Permian extinction reduces them to only a few surviving lineages. From that narrow base, they diversify rapidly during the early Triassic, producing a succession of forms so fast that their fossils become valuable tools for dating rock layers. Their recovery is astonishing because it unfolds while marine environments remain unstable. Ammonoids are active animals, likely requiring substantial oxygen and reliable prey. Some may have lived near the surface, where water was better ventilated. Others could migrate through the water column or move between habitats as conditions changed. Their rapid reproduction and short generation times may have allowed evolutionary experimentation to proceed quickly. Shell shapes alter, ornamentation appears and disappears, and lineages spread across wide regions before vanishing and being replaced. Yet ammonoid diversity repeatedly rises and falls. The group expands after the extinction, suffers during later early Triassic crises, and diversifies again. Its history resembles the carbon isotope record recovery interrupted by renewed disturbance. This makes ammonoids both symbols of resilience and evidence of instability. They can rebound quickly, but they remain vulnerable to the same environmental volatility that creates opportunities for them. Conodont animals also persist through these seas. Their microscopic feeding elements are among the most useful fossils for tracing the Triassic. But the animals themselves are easy to overlook. They were small, eel-shaped chordates, with complex tooth-like structures used for feeding. Different species occupied different depths and water masses, making their remains sensitive indicators of temperature and environmental change. Their eventual extinction at the end of the Triassic will remove a lineage that survived several earlier global crises. Predatory fish begin to diversify as food webs rebuild. Sharks and shark-like cartilaginous fishes survive in reduced numbers, while ray-finned fishes explore new body forms and feeding strategies. Some possess heavy scales and crushing teeth suited to hard-shelled prey. Others become faster swimmers with lighter skeletons and more flexible fins. The spread of shell-crushing predators may encourage prey animals to develop thicker armor, stronger attachment, or new ways of hiding. Even in an impoverished sea, an evolutionary contest is restarting. This renewed predation is one sign that marine ecosystems are becoming more layered. A shell bed alone represents primary consumers filtering water or grazing on microbial films. Add fish that eat those shellfish, and larger predators that eat the fish, and the food web lengthens. But such systems can become top-heavy, containing conspicuous predators supported by a relatively narrow and unstable foundation. A local assemblage may appear modern in complexity while remaining vulnerable to collapse if productivity or oxygen levels shift. The most striking newcomers are reptiles entering the sea. Their ancestors are terrestrial, breathing air and moving on limbs designed for land. The ocean offers food and open ecological space, but it imposes severe challenges. A marine reptile must swim efficiently, control buoyancy, tolerate salt, surface to breathe, reproduce successfully, and regulate body temperature in water that removes heat far faster than air. The transition cannot happen through intention. It unfolds through generations in coastal animals increasingly able to feed and move in shallow marine environments. Among the earliest successful groups are ichthyosaur relatives. Their first forms do not yet possess the sleek dolphin-like bodies of later Jurassic species. Some are elongated and lizard-like, with limbs only partly transformed into paddles. Others already show deeper bodies, stronger tails, and shortened limb bones suited to propulsion and steering. Their fossils appear surprisingly soon after the Great Dying, suggesting that the invasion of the sea and subsequent diversification occur rapidly by evolutionary standards. The speed of this radiation does not mean the process is fully understood. The earlier stages are poorly preserved, and the relationships among several primitive marine reptile groups remain debated. Fossils from China have transformed the picture by revealing small, transitional forms from the early Triassic, but gaps remain between land-dwelling ancestors and fully marine descendants. What survives in the record suggests multiple experiments rather than one clean march from shore to open ocean. Some early marine reptiles feed on fish and squid-like prey. Others specialize in hard shells, using broad teeth to crush bivalves and other armored animals. Sauropterygians begin their own radiation, eventually producing pachypleurosaurs, nothosaurs, placodonts, and later plesiosaurs. Early members often have long bodies, flexible tails, and limbs adapted for a mixture of swimming and movement in shallow coastal settings. They occupy lagoons, shelf seas, and reefless coastlines where prey is returning. Placodonts take one of the strangest paths. Their flattened teeth and powerful jaws are designed for crushing shellfish. Later forms develop broad armor, creating bodies that superficially resemble marine turtles, even though they are not close relatives. This resemblance is an example of convergent evolution. Unrelated animals facing similar problems arrive at similar solutions. A slow-moving shell crusher benefits from protection, weight, and stability near the seafloor. Not all experiments persist. Many marine reptile lineages flourish for only part of the Triassic. Their anatomy may be highly effective within a particular habitat yet vulnerable when sea level, prey, or climate changes. The ocean rewards specialization while conditions remain stable, then punishes it when the environment shifts. The same cycle that shaped land survivors operates beneath the water in a different form. Reproduction creates a crucial boundary. Animals that must return to land to lay eggs remain tied to coastlines. Fully marine life becomes easier when young can be born in the water. Fossils later show that ichthyosaurs give birth to live young, a remarkable adaptation that frees them from beaches and allows permanent occupation of the open sea. Whether the earliest members already reproduced this way is less certain, but live birth likely evolves early in their marine history. The return of a large air-breathing predators reveals how far the sea has come from its immediate post-extinction state. Only a few million years earlier, many regions could barely support stable bottom communities. Now vertebrates pursue prey through coastal waters, ammonoids spread across open seas, and shell-crushing reptiles search the sediment, yet recovery remains patchy. Between productive basins lie waters that are too hot, too stagnant, or too oxygen-poor to sustain similar diversity. Marine life is therefore rebuilding not as a continuous carpet, but as an archipelago of functioning ecosystems. Each favourable shelf, mound, lagoon, and oxygenated corridor supports its own experiment. Some connect as currents carry larvae and adults between them. Others vanish before they can contribute to broader recovery. Through this uneven process, the ocean acquires new inhabitants, new predators, and new relationships that the Permian never knew. The sea has not healed by returning to its former design. It has begun to create another one. Bivalves replace part of the old benthic order. Ammonoids race through cycles of expansion and collapse. Fish develop faster bodies and stronger jaws. Reptiles leave the land and discover that limbs can become paddles. Bones can control buoyancy, and birth can occur far from shore. Beneath a still hostile atmosphere, the first great marine revolution of the Mesozoic is already in motion. The same planet that opens pathways through the sea also creates enormous corridors across the land. Pangaea is not a collection of isolated continents separated by modern oceans. It is one immense supercontinent joined from the far north to the far south, wrapped by Panthalassa and indented along its eastern margin by the Tethys Sea. In theory, an animal could move across distances that would later be broken apart by the Atlantic, Indian, and Southern Oceans. In practice, the journey is controlled by deserts, mountain belts, seasonal rivers, floodplains, and climates that vary sharply with latitude. The land is connected, but it is never uniformly passable. This geography helps explain why closely related Triassic animals appear today in South Africa, India, Antarctica, South America, and other regions now separated by thousands of kilometers of ocean. Lystrosaurus became famous because its remains occur across several southern land masses. The simplest explanation is not that the animal crossed oceans, but that those lands were once joined within Gondwana, the southern portion of Pangaea. The distribution of such fossils later strengthened the case for continental drift, turning extinct animals into evidence that continents themselves had moved. Yet the fossil map is not a complete record of migration. It shows where bones were preserved, discovered, and correctly identified. An animal may have lived across a much larger range than its fossils suggest, while another may appear widespread because river systems concentrated its remains into a few favourable basins. Scholars still debate the true ranges of many Triassic groups because the geological record is patchy and uneven. Trackways offer a different kind of evidence. Bones usually record death, but footprints record movement. A set of impressions may preserve an animal crossing wet mud, turning toward water, or accelerating. The maker is often uncertain because many animals can leave similar prints. Yet tracks reveal posture and gait in ways skeletons alone cannot. Narrow trackways suggest limbs held more directly beneath the body, while broad trackways indicate a more sprawling stance. Across Triassic landscapes, these routes are shaped by water. Rivers descending from uplands cross broad sedimentary basins and spread into braided channels, floodplains, lakes, and seasonal wetlands. During wetter phases, they form green corridors through otherwise dry country. Plants cluster along their banks. Herbivores follow the vegetation, and predators follow the herbivores. Fish and amphibians occupy pools that remain after floods retreat. A river is not simply a source of drinking water. It is a moving line of food, shade, shelter, and migration. The same river can become a trap. Pangaea's climate is strongly seasonal, especially across the interior. Months of drought may be broken by violent monsoonal rain. Channels rise rapidly, sweeping sediment and debris downstream. Floods bury carcasses and create many of the fossil beds known today, but they also erase habitats, redirect channels, and isolate populations. A route used for generations can disappear after one severe season. Monsoon systems develop because the enormous landmass heats and cools differently from the surrounding oceans. The exact strength and reach of these systems remain subjects of climate modelling, but mud cracks, river deposits, evaporate minerals, fossil soils, and plant remains all record alternating wet and dry conditions. Near the coasts and around the Tethys, seasonal moisture supports more continuous vegetation. Deeper within the continent, distance from the sea intensifies aridity. Red beds, dunes, and evaporitic deposits indicate dry environments where water is scarce and soils are oxidized. These interiors are not completely lifeless deserts. Temporary rivers, groundwater-fed oases, and seasonal plant growth create scattered opportunities. But moving through them requires endurance, timing, or the ability to survive long intervals without reliable food. Latitude changes the challenge. Low-latitude regions endure extreme heat, particularly during the early Triassic. Some animals may avoid the hottest zones or remain restricted to wet environments. Higher latitudes offer cooler temperatures but greater seasonality. Near the poles, long summer daylight alternates with prolonged winter darkness, though the climate is generally warmer than that of modern polar regions. Fossil forests and vertebrates from Antarctica show that life occupies these high southern landscapes, but it must adapt to annual cycles unlike those near the equator. Migration across Pangaea therefore does not mean continuous wandering from pole to pole. Most animals probably live within regional ranges defined by river basins, vegetation zones, and seasonal resources. Over many generations, however, populations expand along connected habitats. A species may spread during a cooler or wetter interval, then retreat when heat or drought returns. Range expansion is a slow accumulation of local movements rather than one heroic journey. This process shapes evolution. When populations remain connected, genes and traits move between them. When climate or geography separates them, they begin to diverge. A lineage split between two basins may adapt to different prey, rainfall, or vegetation. If the barrier later disappears, the descendants may meet again as distinct species. Pangaea's connectedness encourages dispersal, while its climatic extremes repeatedly fragment that dispersal. The result is a world that is globally linked and locally experimental. Temnospondyl amphibians demonstrate the importance of freshwater corridors. Their remains appear across broad regions, but their dependence on rivers and lakes makes their distribution sensitive to hydrology. Some lineages likely spread along connected drainage systems during wetter intervals. Others become isolated when basins dry or channels shift. Their success reflects an ability to exploit aquatic networks, yet those same networks can become barriers when drought divides one habitat from another. Terrestrial synapsids follow different routes. Dicynodonts, cynodonts, and other therapsids move through vegetated floodplains and open woodland, tracking food and seasonal water. Their fossils across Gondwana suggest repeated dispersal, between regions that are now separate continents. Heavy-bodied herbivores may depend on continuous forage, while smaller omnivores can cross poorer ground. Burrowing species endure local extremes but may expand slowly. Large predators require territories broad enough to support sufficient prey. Archosaur relatives increasingly exploit open country. More upright limbs make long-distance movement less mechanically costly, though posture alone does not guarantee endurance. Some are lightly built runners, others are massive, armoured, or tied to river margins. Phytosaurs inhabit waterways, while Rauisuchians and other large predators patrol floodplains. Early pterosaurs eventually move above the barriers that constrain terrestrial animals, using flight to cross rivers, coastlines, and broken terrain. Small three-toed footprints appear where dinosaur skeletons are absent, suggesting either wider ranges or similar prints made by close relatives. Their makers remain uncertain, but the trackways record more agile, upright animals moving across open ground. Vegetation shifts with rainfall and temperature, creating a moving map that terrestrial animals must follow. A herbivore's range is ultimately limited by the plants its digestive system can use. The movement of life across Pangaea is inseparable from the movement of climate. During humid intervals, corridors widen. During arid phases, refuges contract, populations meet, separate, and meet again. Extinction removes established occupants from one region, allowing newcomers to enter. Local recovery sends animals outward, while renewed crisis drives them back toward water, altitude, or higher latitude. What appears in the rock record as the sudden arrival of a species may represent thousands of years of expansion along river valleys and basin margins. What looks like disappearance may be retreat beyond the preserved region. The map is constantly changing beneath the animal's feet, not because continents move noticeably within a lifetime, but because rivers shift, deserts grow, vegetation advances, and climates oscillate. Across this connected yet divided world, movement becomes another form of adaptation. Survival belongs not only to bodies capable of enduring harsh conditions, but also to lineages able to find better ones. The paths they follow leave behind bones, spores, and footprints pressed into ancient mud. Those traces reveal a supercontinent functioning as both bridge and barrier, carrying survivors into new habitats while separating them long enough for unfamiliar form to emerge. Where movement opens new territory, competition follows. By the Middle Triassic, the land no longer resembles the nearly empty aftermath of the Great Dying. Riverbanks support thicker vegetation, floodplains hold more herbivores, freshwater channels contain fish, amphibians, and reptiles. Predators that once survived on scattered prey now encounter increasingly crowded ecosystems, and the struggle shifts from simple endurance toward control. The world is still unstable, but it is becoming complex enough for hunters to specialize, grow larger, and compete for the same landscapes. Some of the most imposing predators are temnospondyl amphibians. Their lineage reaches far back into the Paleozoic, and several branches cross the extinction boundary into the Triassic. They're often described as giant salamander-like animals, but the comparison is only approximate. Many possess enormous flattened skulls, broad mouths, and rows of sharp teeth. Their bodies may be short and heavy or elongated and crocodile-like. Some remain small enough to hide among vegetation, while the largest reach several meters in length and dominate lakes, rivers, and wet floodplains. A large temnospondyl does not need to chase prey across open ground. It waits in shallow water with most of its body concealed. Sensory grooves across the skull detect movement. A fish, smaller amphibian or thirsty land animal comes close to the edge, and the broad jaws close with little warning. The strategy depends on patience and location rather than sustained speed. In a landscape organized around seasonal water, control of a river margin can be more valuable than the ability to roam widely. Their skulls reveal remarkable mechanical experimentation. Some have deep notches behind the eyes, broad palates, or tusk-like teeth within the roof of the mouth. When prey is seized, escape becomes difficult. Certain forms possess weak-looking vertebral columns and heavy heads, suggesting that much of the body remains supported by water. Others show stronger limbs and may move more regularly onto land. Scholars still debate the behavior of many species because skeletons can indicate what movements were possible without showing how often those movements occurred. Temnospondyl success is not uniform. Freshwater habitats are vulnerable to drought, sediment, temperature change, and loss of oxygen. A species adapted to permanent lakes may disappear when those lakes shrink. More flexible hunters can move between channels, tolerate muddy water, or survive seasonal drying. Their broad geographic recovery after the extinction suggests that adaptability matters as much as size. Alongside these amphibians, surviving therapsids continue to occupy both predator and prey roles. The synapsid world has been severely reduced, but it has not surrendered the land. Cynodonts, a group more closely related to mammals than Lystrosaurus, become increasingly important. Many are small or medium-sized animals with differentiated teeth, powerful jaw muscles, and limbs held more directly beneath the body than those of earlier synapsids. Some eat insects and small vertebrates. Others become herbivores or omnivores. Their diversity hints at a future that is not yet visible. Predatory cynodonts possess incisors at the front of the mouth, enlarged canine teeth, and smaller slicing teeth behind them. This division of labor allows food to be processed more efficiently than with a row of nearly identical teeth. The jaw joint and hearing structures are also undergoing gradual changes that will eventually contribute to mammalian anatomy. Though these transformations unfold over immense spans of time, in the Triassic, they simply make cynodonts effective feeders with increasingly precise bites. Some may possess hair or hair-like insulation, but direct evidence is rare. Small body size and potentially elevated metabolism would make insulation useful, especially during cool nights or at higher latitudes. Whisker-like sensory systems may also have appeared within the lineage, yet the exact timing remains uncertain, and it is safer to imagine a range of coverings and metabolic strategies rather than every cynodont as a furry miniature mammal. The larger predatory stage increasingly belongs to archosauriforms. These are reptiles belonging to or closely surrounding the lineage that will later divide into crocodilian and bird branches. Their Triassic diversity is far greater than the surviving modern groups suggest. Some walk on 4 sprawling limbs, others stand upright. Some are heavily armoured, while others are lightly built runners. They occupy river systems, dry uplands, coastal plains, and forested margins. Among the most unusual are pterosaurs. Their long snouts, conical teeth, armoured backs, and semi-aquatic habits make them look remarkably like crocodiles. Yet the nostrils sit high on the skull near the eyes rather than at the tip of the snout. Pterosaurs are not crocodiles, and their resemblance results from similar adaptation to ambush hunting in water. They wait along river margins, feeding on fish and terrestrial animals, while thick osteoderms protect the body. The existence of pterosaurs beside large temnospondyls creates potential ecological overlap. Both may hunt in rivers and attack similar prey. Whether they directly compete in every region is impossible to know, but their coexistence suggests that Triassic waterways contain multiple large predators divided by prey size, water depth, hunting style, or season. One may dominate deeper channels while another occupies marshes or lake margins. Complex ecosystems allow similar predators to persist only when some separation reduces constant conflict. On land, erythrosuchids and related archosauriforms develop enormous skulls and powerful jaws. These animals appear relatively early in the Triassic and can become the dominant terrestrial predators in some regions. Their heads are disproportionately large, packed with recurved teeth capable of gripping flesh. Strong neck muscles help support the weight. Their limbs are not yet as fully upright as those of later archosaurs, but they represent a major escalation in predator size after the extinction. Later come Rauisuchians and other pseudosuchians from the crocodilian side of the archosaur family tree. Some grow into towering predators with deep skulls, serrated teeth, and limbs held beneath the body. Their posture gives them a higher stance and may improve sustained movement. A few forms can move on two legs for at least part of the time, while others remain powerful quadrupeds. They are not dinosaurs, though their appearance can seem more dinosaur-like than that of many early dinosaurs living beside them. Their success reveals an important truth about the Triassic. Dinosaurs do not immediately take command when they first appear. For much of the period, they're only one component of a broader archosaur radiation. Large pseudosuchian predators often occupy the highest terrestrial hunting roles. Armored herbivorous relatives graze or browse nearby. Crocodile-line archosaurs, not dinosaurs, dominate many ecosystems in both variety and body size. Predation itself begins reshaping prey. Herbivores that survive the earliest recovery often rely on abundance, broad diets, or burrowing. As predators become faster and more specialized, prey animals face new pressures. Armor thickens in some lineages, limbs become stronger or more upright. Herding may offer protection, though direct evidence for social behavior is difficult to establish. Greater body size discourages smaller hunters, but demands more food. Burrows become defensive structures as well as shelters from climate. Pterosaurs take protection to an extreme. These pseudosuchians are generally herbivorous or omnivorous rather than predators, but their bodies are covered in heavy armor arranged across the back and sides. Some species possess spikes projecting from the shoulders or flanks. Their skulls are relatively small, and their snouts may be suited to rooting through soil or feeding on low vegetation. They share landscapes with large hunters whose teeth are capable of inflicting serious damage, and armor offers one solution to that threat. Dicynodonts also continue beyond the age of Lystrosaurus. Later forms include massive herbivores with powerful beaks and heavy bodies. Some reach the size of large modern mammals, providing substantial prey for the largest archosaur predators. Their survival shows that synapsids remain ecologically important even as archosaurs expand. The Triassic land world is not a simple replacement of one ruling group by another. It is a prolonged overlap in which old lineages persist while new ones diversify around them. Evidence of direct interaction is rare but occasionally dramatic. Bite marks on bones may indicate predation or scavenging. Broken teeth embedded in skeletons can identify an attacker more precisely. Coprolites, fossilized feces, preserve bone fragments, scales, or shells, and reveal what predators consumed. Trackways may show multiple animals moving through the same area, though they rarely record an actual chase. Each clue captures only a moment, and no single fossil can reconstruct an entire food web. Scavenging is likely common. In environments where prey populations fluctuate, a carcass is too valuable to ignore. Large predators may drive smaller hunters away, while small animals strip remains after the larger feeders leave. Teeth designed for killing can also tear flesh from animals already dead. The distinction between predator and scavenger is rarely absolute in modern ecosystems, and was probably no clearer in the Triassic. As food webs lengthen, competition becomes more intense but also more structured. Rivers support aquatic ambush hunters. Open floodplains favour mobile terrestrial predators. Smaller cynodonts search for insects and vertebrates in undergrowth or burrows. Nocturnal activity may reduce encounters with larger hunters and allow access to prey overlooked during the day. Different body sizes and hunting schedules divide the landscape into overlapping zones of danger. This complexity is one of the strongest signs that recovery is advancing. A devastated ecosystem cannot support many large predators because energy is lost at every step of the food chain. Plants must first become abundant enough to sustain herbivores, and herbivores must become numerous enough to sustain hunters. The rise of multiple predator guilds therefore indicates deeper productivity beneath the visible violence. Yet the balance remains temporary. Climate shifts, volcanic disturbances, droughts, and changing rivers repeatedly rearrange which hunters hold power. A lineage dominant in one basin may be absent in another. A predator perfectly adapted to a wet floodplain may vanish when aridity expands. No group controls the whole supercontinent. The Triassic landscape is becoming crowded, but it has not settled on a permanent ruler. Giant amphibians watch from muddy water. Therapsids hunt among vegetation and shelter underground. Phytosaurs occupy the channels. Erythrosuchids and Rauisuchians patrol the banks and open ground. Early dinosaurs remain smaller figures moving through the same unstable world. The struggle is no longer only against heat and hunger, it is against other survivors, each carrying a different answer to the question of what a predator can become. The competition among Triassic predators is only one part of a much larger anatomical upheaval. Across Pangaea, reptile bodies begin to explore possibilities that had rarely existed before the Great Dying. Limbs move beneath the torso, necks lengthen to improbable proportions, teeth become crushing plates, shearing blades, pegs, or beak-like cutting edges. Armour spreads across backs and flanks. Some animals become climbers, others swimmers, runners, diggers, or gliders. The Triassic is not yet a world organised around a few familiar designs. It is a workshop filled with prototypes, many of which will disappear without leaving descendants. This experimentation is possible partly because extinction has removed so many established competitors. Ecological space remains open, and no single group controls every habitat. A body plan that might have been excluded in a crowded Permian ecosystem can now spread long enough to become specialized. The result is not a steady march toward dinosaurs or mammals. Evolution moves sideways, producing successful forms whose anatomy leads nowhere beyond the Triassic. Posture is one of the most important changes. Earlier reptiles and amphibians generally move with limbs extending outward from the sides of the body. This sprawling arrangement is stable and effective, especially for low, slow movement, but it causes the torso to bend laterally with each step. As several Triassic lineages bring the limbs closer beneath the body, they reduce this side-to-side motion. The trunk becomes more stable, stride length increases, and sustained movement becomes easier. Archosaurs achieve upright posture in more than one way. On the crocodilian side of the family tree, the hip and upper leg are arranged so that the femur can stand nearly vertical beneath the body. On the dinosaur side, the joint develops differently, with the head of the femur fitting inward into a more open hip socket. both systems produce an elevated stance, but they are not identical. The distinction is hidden beneath skin and muscle, yet it will shape the later history of each lineage. An upright body is not automatically fast. Some massive Rhesuchians stand tall but remain heavy. Deliberate predators, pterosaurs, carry armor that limits agility. Other archosaurs become lightly built runners with narrow bodies and long hind limbs. The new posture simply expands what locomotion can become. Once the torso is raised from the ground, legs can lengthen, stride can increase, and the forelimbs can begin to perform tasks other than supporting weight. Bipedality emerges from this shift. Several Triassic archosaurs, including early dinosaur relatives, can move on two legs. A long tail balances the body behind the hips, while powerful hind limbs provide propulsion. The forelimbs remain free to grasp, stabilize prey, or assist during slower movement. Some animals may alternate between two-legged running and four-legged walking. Fossil trackways preserve this variety, but identifying the exact track maker remains difficult. At the opposite extreme are reptiles that become increasingly specialized for climbing. Dinosaurs possess deep bodies, grasping hands, and highly unusual tails. In some species, the tip of the tail ends in a claw-like structure that may help anchor the animal to branches. Their forelimbs are powerfully built, and one enlarged claw may have been used to tear into bark or decaying wood in search of insects. They have sometimes been compared with chameleons or anteaters, but the resemblance is superficial. Dinosaurs represent a uniquely Triassic solution to life above the ground. Their skeletons are so strange that early specimens were difficult to interpret. Isolated bones were mistaken for parts of unrelated animals, and the true anatomy became clear only when more complete fossils were found. The confusion is understandable. Evolution rarely produces a body that fits neatly into categories invented hundreds of millions of years later. What survives in the record suggests a reptile that climbs slowly, braces itself with a muscular tail, and searches tree trunks for food in a world where arboreal niches are still largely unexplored. Other reptiles stretch the neck rather than reshape the tail. Tanystropheus is the most dramatic example. Its neck is longer than its body and formed from only a small number of enormously elongated vertebrae. For decades, paleontologists debated whether it lived mainly on land or in water. Its rigid neck seems poorly suited to rapid movement, and its body proportions appear almost mechanically unreasonable. Recent interpretations favor a largely aquatic or shoreline lifestyle for at least some species, with the long neck used to approach fish or squid-like prey while the bulk of the body remained farther away. Even within Tanystropheus, different species appear to occupy different feeding roles. Smaller forms possess teeth suited to softer prey, while larger ones carry stronger jaws and more robust teeth. This division may have reduced competition between animals sharing the same coastal habitats. The evidence remains incomplete, but the genus demonstrates how far natural selection can extend one part of the skeleton when a particular feeding strategy rewards it. Rhinoceros pursue a different form of specialization. These stout herbivorous archosauromorphs become extremely abundant in parts of the Middle and Late Triassic. Their skulls are broad, their beaks powerful, and their jaws equipped with multiple rows of teeth that create crushing surfaces. As the jaws close, food is trapped and processed between grooved tooth plates. The arrangement is well suited to tough vegetation, possibly including seed ferns and other plants growing in seasonal environments. The teeth are not replaced in the familiar reptilian manner. New tooth rows are added toward the rear as the jaws grow, while older surfaces wear down toward the front. The skull effectively carries its own moving field of grinding structures, This system works so well that rhynchosaurs can dominate herbivore communities, sometimes accounting for the majority of large-bodied fossils in a formation. Yet their specialization may later become a vulnerability when vegetation changes. Trilophosaurs develop another unusual feeding apparatus. Their broad teeth possess multiple cusps arranged for crushing plant material rather than slicing flesh. The skull lacks teeth at the front, creating a beak-like region, while the rear teeth process food with repeated pressure. These reptiles are neither dinosaurs nor close mammalian relatives. They belong to one of several archosauromorph branches that flourish in the Triassic and then disappear. Armor evolves repeatedly. Pterosaurs carry rows of interlocking bony plates across the body, sometimes reinforced by spikes. Placodonts in the sea develop broad shells and heavy ribs. Small terrestrial reptiles acquire osteoderms that protect the back without producing the full weight of a tank-like body. Armor is an expensive investment. It requires minerals, energy, and structural support, but it allows slow-moving herbivores or shell crushers to survive attacks that faster animals avoid through speed. Feeding structures become equally diverse. Beaks crop vegetation. Peg-like teeth hold slippery fish. Flattened teeth crush shells. Serrated blades slice flesh. Some reptiles lose teeth entirely from parts of the jaw, while others pack the mouth with repeated rows. These designs reflect a world in which food sources are expanding but remain unevenly distributed. A specialist can flourish wherever its preferred resource is abundant. Yet its success may collapse when climate or vegetation shifts. The respiratory system likely changes alongside posture and activity. More upright archosaurs can move without compressing the lungs as strongly through lateral body bending. Directional airflow may improve gas exchange, while air-filled spaces begin to enter parts of the skeleton in some lineages. Direct evidence is limited, especially among early forms, but the anatomical foundation for later archosaur respiratory efficiency is taking shape. Breathing, movement, and feeding are not independent. A predator capable of sustained pursuit needs efficient lungs, strong hind limbs, and a skull light enough to carry while running. A heavily armored herbivore can tolerate slower breathing and movement if protection allows it to feed safely. A climber requires balance, grasping feet, and a body light enough for branches. Each organism is an integrated compromise rather than a collection of isolated traits. Some of the most consequential experiments begin in small bodies. Lightweight skeletons, elongated fingers, and membranes of skin eventually allow pterosaurs to become the first vertebrates capable of powered flight. Their earliest fossils appear in the late Triassic, already equipped with wings, leaving the initial stages of the transformation obscure. The fourth finger is greatly lengthened to support the main flight membrane, while the other fingers remain free for gripping. Hollow bones reduce weight, and the chest supports powerful flight muscles. Pterosaurs are not dinosaurs, though they are close relatives. Their appearance marks an ecological breakthrough greater than simple gliding. Powered flight allows movement across rivers, coastlines, forests, and barren ground without following terrestrial corridors. It provides access to insects, fish, and elevated resting sites. Yet the origin of flight remains one of the Triassic's unresolved problems, because the transitional forms are missing. Many other experiments vanish more completely. Long-necked shoreline hunters, armored rooters, beaked herbivores, tree-climbing reptiles, and giant pseudosuchian predators leave no living descendants. Their extinction can make them seem like failed designs. But that judgment is distorted by hindsight. Some flourish for tens of millions of years, longer than many familiar modern lineages have existed. The Triassic revolution is not a contest to produce the one correct reptile. It is an expansion of anatomical possibility. The devastated world has become a place where almost every part of the vertebrate body can be reconsidered. Limbs change direction. Lungs move air differently. Teeth become tools of extraordinary precision. Skin stretches into wings. Bony plates turn animals into moving fortresses. Necks extend beyond proportions that seem practical, yet function well enough to persist. Among this crowd of successful oddities, the earliest dinosaurs remain modest. They possess no obvious guarantee of future dominance. They're simply another experiment, lightly built and relatively rare, moving through ecosystems already occupied by animals whose bodies seem every bit as capable. Only later will extinction and opportunity reveal which design has been waiting at the margins. The animals waiting at those margins do not arrive as giants. They do not shake the ground, tower above forests, or immediately drive other predators away. The earliest dinosaurs appear as relatively small, lightly built creatures moving through ecosystems already dominated by larger archosaurs, dysynodont herbivores, rhynchosaurs, synodonts, and amphibious hunters. Their beginnings are so modest that, without knowledge of what follows, they would seem like only one more branch in the crowded evolutionary experimentation of the Triassic. The oldest widely accepted dinosaur fossils date to roughly 233 million years ago, during the late Triassic, though possible earlier remains remain disputed. Many of the most important discoveries come from Argentina and Brazil, where rocks preserve animals such as Eoraptor, Herrerasaurus, Saturnalia, Bureolestes, and their close relatives. These forms do not fit neatly into the later categories of enormous long-necked herbivores, armored plant-eaters, and giant carnivorous theropods. They stand near the base of the dinosaur family tree, where familiar distinctions are only beginning to emerge. Some are no larger than a medium-sized dog. Others reach several meters in length but remain slender compared with the massive predators living beside them. Their hind limbs are long and positioned beneath the body. Their ankles and hips are adapted for upright movement. The tail extends behind as a counterbalance, while the forelimbs are shorter and often equipped with grasping hands. These proportions allow efficient bipedal locomotion, though some early forms may have moved on four limbs during slower activity or feeding. The dinosaur hip is one of the most important pieces of this design. The head of the femur turns inward into a socket that is open, or becoming open, allowing the leg to swing beneath the body rather than outward. This arrangement supports a narrow gait. Trackways attributed to small dinosaur-like animals show footsteps placed close to the body's midline, indicating efficient forward movement. Such locomotion reduces wasted side-to-side motion and may be useful for running, migration, or covering large territories. Yet upright posture is not unique to dinosaurs. Several pseudosuchians and other archosaurs also stand tall and move efficiently. Nor are early dinosaurs always the fastest animals in their environments. Their success cannot be explained by one simple anatomical advantage. They combine several useful traits, but many competitors possess their own equally effective combinations. Their skeletons tend to be relatively lightweight. Hollow spaces appear in some bones, particularly in forms related to later theropods. These spaces may connect to parts of the respiratory system, though the full extent of air sacs in the earliest dinosaurs remains debated. A lighter body reduces the energy needed for movement, while efficient breathing could support sustained activity. The evidence remains incomplete, but the foundations of the highly effective dinosaurian respiratory system are likely already present in some form. Growth also appears to be comparatively rapid. Microscopic studies of early dinosaur bones often show highly vascularized tissue, indicating fast deposition during favorable periods. Growth may pause seasonally, leaving lines within the bone, but the overall pattern suggests that some dinosaurs reach maturity faster than many contemporary reptiles. Rapid growth can reduce the time spent at vulnerable juvenile sizes and allow populations to recover after local decline. This does not mean every dinosaur grows quickly or maintains a high constant metabolism. Early species show considerable variation. Their physiology likely occupies a range between the slower growth of many modern reptiles and the sustained high metabolism of birds. Scholars still debate exactly how warm-blooded the earliest dinosaurs were, partly because metabolism does not fossilize directly. Bone texture, posture, respiratory anatomy, and growth rates provide clues, but none offers a complete answer alone. The diet of the first dinosaurs is equally varied. Herrerasaurus is a sharp-toothed predator with a deep skull and grasping hands. Its jaws carry serrated teeth suited to slicing flesh, while its hind limbs support active pursuit. Eoraptor has a more mixed set of teeth, some pointed and others broader, suggesting an omnivorous or generalized diet. Saturnalia and Bureolestes belong near the ancestry of sauropodomorphs, the lineage that will eventually produce the largest land animals in history. Yet these early members remain small, lightly built, and at least partly carnivorous or omnivorous. This shift is especially revealing. The ancestors of later giant herbivores do not begin as enormous plant eaters. Their evolution involves gradual changes in skull shape, teeth, neck length, digestive capacity, posture, and body size. Early sauropodomorph relatives possess grasping hands and narrow skulls, while later forms develop stronger herbivorous adaptations and increasingly large bodies. The transformation is not a single leap, but a sequence of experiments spread across millions of years. The earliest ornithischians, the broad group that will later include stegosaurs, ankylosaurs, ceratopsians, and duck-billed dinosaurs, are much harder to identify. Some fragmentary late Triassic fossils have been assigned to the group, but their relationships remain controversial. Tiny teeth and incomplete skeletons can be difficult to distinguish from those of other archosaurs. What survives in the record suggests that the major dinosaur lineages begin separating during the Triassic, but the timing and sequence remain uncertain. Footprints may push the story deeper. Three-toed tracks with narrow gaits occur in rocks older than the oldest unquestioned dinosaur skeletons. Some may have been made by true dinosaurs, while others belong to close dinosauriform relatives that walked in similar ways. A footprint reveals the shape of the foot and the style of movement, but not the entire skeleton. Without associated bones, the identity of the maker remains uncertain. These close relatives are important because dinosaurs do not emerge from nowhere. They belong to a broader group of small, upright archosaurs called dinosauromorphs. Animals such as Lagopithecus, Marsuchus, and Silosaurus possess combinations of traits approaching the dinosaur condition. Some are agile runners. Others may be quadrupedal herbivores or omnivores. Their existence turns dinosaur origins into a gradual evolutionary transition rather than a sudden appearance. Silosaurids are especially difficult to place. They have long limbs, lightly built bodies, and jaws adapted in some species for plant material. Some researchers regard them as close relatives just outside Dinosauria, while others argue that they may belong within the earliest Ornithischian branch. The debate matters because it changes how the first dinosaurian herbivores are reconstructed. It also illustrates a larger problem. Nature does not preserve the clean boundaries that later classification tries to impose. By the time recognizable dinosaurs appear, they are already geographically dispersed. Fossils occur across South America, Africa, India, Europe, and North America. Though the quality and age of the records vary, Pangaea allows relatively rapid expansion through connected lowlands and river basins. Climatic belts still restrict movement, but there are no Atlantic or Indian Oceans dividing populations as they will later. Despite this reach, dinosaurs remain uncommon in many late Triassic assemblages. At some sites, they account for only a small proportion of the vertebrate fossils. In a roughly 209 million-year-old ecosystem preserved in what is now Petrified Forest National Park in Arizona. A diverse community includes pterosaurs, early turtles, frogs, phytosaurs, croc-line archosaurs, and other reptiles, while dinosaurs appear absent from the particular assemblage. Whether this reflects habitat preference, local rarity, sampling, or preservation is uncertain, but it confirms that dinosaurs do not dominate every landscape. Elsewhere, early dinosaurs coexist with much larger competitors. A small predatory dinosaur may hunt insects, reptiles, or young animals while Rauisuchians control larger prey. Early herbivorous forms feed among rhynchosaurs and synodonts already well established in plant-eating roles. Dinosaurs occupy parts of the ecosystem rather than replacing it wholesale. Their early advantages may lie in flexibility. Lightweight bodies require less food than those of giant predators. Upright limbs make long-distance movement efficient. Rapid growth and broad geographic distribution help populations recover from environmental disturbance. Some may reproduce in relatively large numbers, though direct evidence from the earliest dinosaurs is scarce. Others exploit smaller prey or vegetation overlooked by larger animals. Climate may also favour them unevenly. Dinosaurs appear to spread more successfully in some regions after environmental disruptions reduce competitors. During stable intervals, established archosaur groups remain dominant. This pattern suggests that dinosaur expansion depends not only on anatomy, but also on ecological opportunity created by repeated crisis. A lineage can possess useful traits for millions of years without becoming dominant until the world changes around it. The first dinosaurs therefore offer no clear sign of the future. Nothing in Eoraptor's small frame announces the later arrival of Tyrannosaurus. Nothing in the lightly built early sauropodomorphs predicts animals weighing many tens of tons. Their importance becomes visible only retrospectively, after later extinction removes competitors and opens new habitats. For now, they remain quiet participants in a Triassic world that belongs to no single dynasty. They run beneath larger predators, feed beside older herbivore lineages, and leave sparse bones in river deposits. Their anatomy is efficient, their growth often rapid, and their geographic range broad. But none of this guarantees success. The future age of dinosaurs begins not with conquest, but with survival at the edge of ecosystems shaped by animals that still seem far more powerful. The future does not belong to dinosaurs simply because they are better designed. That explanation is attractive because it turns evolution into a contest with a clear winner, but the Triassic record resists such simplicity. Archosaurs flourish while many synapsids and amphibian lineages decline. Yet the shift unfolds unevenly across millions of years and different environments. In some regions, crocodile-line archosaurs dominate long before dinosaurs do. In others, dysynodonts, synodonts, rhynchosaurs, and temnospondyls remain abundant. No single anatomical innovation, climatic event, or competitive encounter fully explains the transition. One possibility is straightforward competition. Archosaurs may have moved more efficiently, grown more rapidly, breathed more effectively, or reproduced in ways that allowed them to outcompete older lineages. Their increasingly upright limbs reduce lateral bending of the torso and permit longer strides. Some appear capable of sustained activity across open ground. If parts of their respiratory system already produce directional airflow, they may also have extracted oxygen more efficiently than many contemporaries. These traits could matter greatly in a hot world where warm air, low oxygen availability, and long seasonal migrations place pressure on active animals. Yet direct evidence of competition is difficult to find. Fossils rarely preserve two species struggling over the same resource. Even when groups overlap in time and place, they may divide food, habitat, or activity periods in ways the skeleton does not reveal. A large temnospondyl in a river and a lightly built archosaur on the floodplain are not necessarily competitors. A dicynodont cropping low vegetation may use different plants from a rhynchosaur crushing tougher material. Coexistence can persist for millions of years when ecological roles overlap only partially. Competition also cannot explain why successful archosaur groups sometimes vanish, while supposedly inferior synapsids survive. Many pseudoseuchians develop upright posture, efficient movement, armor, and powerful jaws, yet most disappear before the Jurassic. Cynodonts remain relatively small and inconspicuous, but ultimately give rise to mammals. Evolutionary survival does not consistently reward the most imposing organism in the present ecosystem. Climate offers another explanation. Archosaurs may be better suited to the hot, strongly seasonal conditions of the Triassic. Some researchers have suggested that differences in water conservation, egg structure, respiratory efficiency, or tolerance of aridity allowed them to spread through dry interiors where amphibians and many therapsids were restricted. Reptilian skin generally limits water loss more effectively than amphibian skin, while shelled eggs reduce dependence on open water for reproduction. These features are not unique to archosaurs, but they may help explain why reptile lineages expand across increasingly seasonal landscapes. Temnospondyls remain tied to fresh water to varying degrees. Even species capable of moving over land need suitable aquatic habitats for feeding or reproduction. When lakes shrink and river systems become intermittent, their populations fragment. A lineage that dominates a permanent wetland may have little access to neighboring basins once aridity separates them. Archosaurs able to cross dry ground can follow shifting food and water across larger territories. This does not make amphibians passive victims of climate. Temnospondyls survive throughout the Triassic and occupy high latitude, low latitude, terrestrial, and aquatic settings. Some tolerate seasonal environments remarkably well. Their decline is gradual and geographically uneven. In certain ecosystems, they remain major predators even as archosaurs diversify around them. The evidence suggests restriction rather than immediate replacement. Synapsids face a different set of pressures. Many large herbivorous therapsids depend on substantial plant biomass. When vegetation changes, their specialized feeding systems may become less effective. Dicynodont beaks and jaw muscles handle certain kinds of tough material well, but a shift in dominant plant communities can favor new herbivores with different teeth and digestive strategies. Large bodies also demand reliable food over broad areas. During drought, smaller and more mobile species can survive on resources too scattered to support giants. Still, synapsids do not decline as one unified group. Dicynodonts remain important well into the late Triassic, and some become enormous. Cynodonts diversify into insectivores, carnivores, omnivores, and herbivores. Several lineages develop increasingly mammal-like jaws, teeth, and perhaps insulation. Their ecological importance may be underestimated because small bones preserve less readily and are harder to discover than the skulls of large archosaurs. The fossil record itself can create an illusion of replacement. River deposits preserve large animals more often than tiny burrowers. Armoured plates, robust teeth, and thick limb bones survive processes that destroy delicate skeletons. A formation rich in phytosaurs and etosaurs may still have supported numerous small cynodonts, whose remains were scattered or consumed. Apparent archosaur dominance may therefore reflect both genuine abundance and preservational bias. Another explanation focuses on growth. Bone histology indicates that many archosaurs grow rapidly during favourable seasons. Fast growth allows juveniles to pass quickly through vulnerable sizes and may shorten the time before reproduction. Populations recovering after drought or local extinction could rebound more quickly. Some therapsids also grow rapidly, however, and growth rates vary widely within each group. There is no clear line separating fast archosaurs from slow synapsids. Reproduction may have mattered even more, though the evidence is scarce. Large clutches could produce many offspring during brief favourable intervals. Nesting away from water could open habitats unavailable to amphibians. Eggs resistant to water loss would help in dry regions, but too rigid or heavily mineralized a shell introduces its own risks. Embryos need gas exchange, stable temperature, and sufficient moisture. Without nests, eggs, or embryos for most Triassic groups, comparisons remain largely inferential. Respiratory efficiency remains one of the strongest but most debated possibilities. Modern birds and crocodilians both possess forms of directional airflow through the lungs, suggesting that the common ancestor of archosaurs may already have had a more efficient breathing system than once assumed. In hot climates, efficient gas exchange supports activity and helps remove excess heat. It may also provide resilience when atmospheric oxygen is lower than modern levels. But the lungs themselves do not fossilize, and the earliest archosaur respiratory anatomy must be reconstructed indirectly. Hollow bones, rib shape, vertebral structure, and comparison with living relatives provide clues, not certainty. Even if archosaurs breathe more efficiently, that advantage does not operate in isolation. Food supply, body size, behavior, and habitat still determine whether a lineage succeeds. The structure of the heart and circulation may also differ among groups, influencing endurance and heat tolerance. Living crocodilians have a 4-chambered heart with specialized blood flow control, while birds possess high-pressure circulation suited to intense activity. Some elements of this cardiovascular sophistication may reach back into Triassic archosaurs. Yet again, soft tissues are lost, and conclusions remain cautious. A more powerful explanation may lie not in superiority, but in repeated disturbance. Stable ecosystems favour established specialists. Unstable ecosystems repeatedly remove them. Archosaurs appear particularly effective at expanding into newly open space after droughts, extinctions, and climatic shifts. Their wide distributions, varied diets, and range of body sizes allow some member of the group to survive when another fails. The advantage belongs to the diversity of the whole radiation rather than to one perfect archosaur body. This is ecological opportunism on a continental scale. When a river basin dries, aquatic forms decline, but terrestrial runners may spread. When vegetation changes, one herbivore lineage disappears while another with a different feeding apparatus expands. When large predators vanish, smaller hunters grow in size or move into their territories. Archosaurs repeatedly supply candidates for vacant roles because they are already experimenting with so many forms. Synapsids and amphibians also experiment, but many of their successful lineages remain concentrated within narrower ecological zones. Temnospondyls are strongest around freshwater. Large dicynodonts depend on vegetation sufficient to sustain heavy bodies. Small cynodonts are flexible, but their size keeps them from occupying the largest herbivore and predator roles in many ecosystems. This division is not absolute, yet it shapes which groups benefit when environments are rearranged. Historical contingency may be the most important factor of all. The Great Dying removes species without regard to future potential. A lineage survives because one population happens to occupy a refuge, reproduce at the right time, or avoid the most severe regional stress. Later crises repeat the sorting. Traits matter, but chance determines which traits remain available for selection. An archosaur lineage may inherit a landscape not because it defeated every competitor, but because drought removes those competitors first. A cynodont may survive unnoticed in a burrow while a dominant predator disappears. Once populations become small, random events such as disease, failed breeding seasons, or local floods can decide whether an entire branch continues. The grand pattern of evolution is built partly from such local accidents. There is also no single moment when archosaurs take control. The transition differs between continents and habitats. In some late Triassic assemblages, pseudosuchians dominate. In others, rhynchosaurs or dicynodonts provide most of the herbivore biomass. Dinosaurs increase in abundance at different rates, and some ecosystems preserve almost none. The phrase rise of the dinosaurs compresses a long, irregular process into a misleading upward line. The competing explanations are therefore not mutually exclusive. Upright posture improves movement. Efficient breathing may support endurance. Reproduction away from water broadens habitat. Rapid growth aids recovery. Climate weakens some competitors. Extinction creates vacancies. Geographic range spreads risk. Chance preserves one lineage while erasing another. Together, these forces gradually alter the balance. What appears from a distance as the replacement of an old world by a superior new one is, at closer range, a sequence of local victories, retreats, accidents, and environmental filters. Archosaurs flourish not because evolution has chosen them, but because repeated crises continually reshape the rules in ways that some of their many forms can exploit. Synapsids and amphibians do not simply lose, they retreat into habitats and body sizes where their descendants will continue on different terms. For much of the Triassic, the outcome remains uncertain. Giant amphibians still control waterways. Dicynodonts still dominate some herbivore communities. Crocodile-line archosaurs occupy the largest predatory roles. Dinosaurs remain one branch among many. The world has not yet delivered its final verdict, and the next major disruption will not merely reward the groups already strongest. It will change the environments in which strength is measured. The next disruption arrives not as a return to the arid furnace of the early Triassic, but as water. Across regions accustomed to strong seasonality and long dry intervals, rainfall intensifies, rivers enlarge, floodplains spread, lakes deepen, and sediment pours from newly eroded landscapes into coastal seas. The change does not affect every part of Pangaea in the same way, or begin everywhere at precisely the same moment, but its geological traces appear across enough regions to reveal a major disturbance. This is the Carnian pluvial episode, an interval of climatic upheaval roughly 234 to 232 million years ago that interrupts the late Triassic and rearranges ecosystems on land and in the sea. The name can sound deceptively gentle. A pluvial episode suggests rain returning to a thirsty world, and in some places increased moisture undoubtedly creates new habitats. Yet the event is not simply a long season of beneficial rainfall. It is a sequence of humid pulses tied to warming, changes in the carbon cycle, intensified weathering, and repeated ecological disruption. Dry-adapted communities contract, rivers become unstable, coastal waters receive heavy loads of sediment and nutrients. Organisms that flourish under one set of conditions may disappear when the climate swings again. Before this interval, many continental interiors support strongly seasonal landscapes dominated by drought-tolerant vegetation and animals adapted to open, often arid environments. Rhinoceros are among the most conspicuous large herbivores in several regions. Their broad skulls, powerful beaks, and complex tooth plates make them highly effective processors of tough plants. Decinodonts remain important elsewhere, while etosaurs, cynodonts, pseudosuchians, early dinosaurs, and temnospondyls divide the available habitats. These communities are not static, but they have developed around predictable seasonal stress. Then rainfall patterns begin to change. In sedimentary basins, layers associated with dry soils and evaporative conditions give way to deposits formed by stronger rivers, deeper lakes, and wetter floodplains. Clay minerals indicate more intense chemical weathering. Fossil soils change character. Organic rich layers appear where stagnant water preserves plant matter. Marine records show parallel carbon isotope disturbances, suggesting that the event is connected to a broader reorganization of the atmosphere-ocean system, rather than a collection of unrelated regional floods. Large-scale volcanism is the leading suspect. Around the same time, enormous eruptions build the Pangaea oceanic plateau in a region that will eventually become part of western North America. Lava spreads across the sea floor in volumes capable of releasing substantial greenhouse gases. Carbon dioxide drives warming, while volcanic emissions and climate feedbacks alter the global carbon cycle. Warmer conditions increase evaporation from the ocean, and a warmer atmosphere can carry more moisture. The hydrological cycle intensifies, producing heavier rainfall in some regions even as others remain dry. The exact connection remains debated. Dating volcanic rocks and sedimentary climate signals to within a few 100,000 years is difficult, and the Carnian pluvial episode may consist of several pulses rather than one continuous event. Other mechanisms, including changes in ocean circulation and orbital forcing, may modify the response. What survives in the record suggests a strong relationship between volcanism, carbon cycle disruption, warming, and rainfall, but no single explanation fully accounts for every regional pattern. The rain transforms the land unevenly. In areas where vegetation expands, denser plant cover stabilizes soils and creates new feeding opportunities. Ferns, conifers, seed ferns, and other plants respond differently depending on latitude, elevation, and drainage. Some dry-adapted floras decline, while moisture-loving forms spread along rivers and lowlands. Forest structure changes, altering shade, ground cover, and the distribution of food. These botanical shifts can destabilize highly specialized herbivores. Rhinoceros are extraordinarily successful before and during parts of the Carnian, yet many lineages decline around this broader interval. Their disappearance has sometimes been linked to changes in vegetation, especially the replacement of plants suited to their feeding apparatus. That explanation is plausible, but incomplete. Fossil plant records are patchy, and rhinoceros decline does not occur simultaneously everywhere. Climate, competition, habitat loss, and regional extinction probably interact. Dinosaurs appear to benefit from the rearrangement. though not as suddenly or universally as older narratives once suggested. In several regions, dinosaur abundance and diversity increase after the Carnian disturbances. Early sauropodomorphs expand as herbivores, while theropods occupy a wider range of predatory roles. Their upright posture, efficient movement, rapid growth, and broad geographic distribution may help them exploit newly reorganized environments. But the Carnian pluvial episode does not instantly hand the planet to dinosaurs. Pseudoseuchians remain diverse and often dominant. Large amphibians persist. Descenodonts continue in some regions. Dinosaurs rise at different rates in different basins, and their apparent expansion may partly reflect changes in preservation and sampling. The event creates opportunity, but opportunity is filtered through local ecology. One of the most consequential developments is the growing importance of sauropodomorph herbivores. Their earliest relatives are small and often omnivorous, but later Carnian and post-Carnian forms begin increasing in size, lengthening the neck, and relying more heavily on plants. A longer neck expands the feeding envelope without requiring the whole body to move. A large digestive system can process abundant low-quality vegetation through fermentation. Greater size reduces vulnerability to smaller predators and allows longer journeys between feeding areas. These adaptations do not appear all at once, and the first sauropodomorphs remain far from the gigantic sauropods of the Jurassic, yet the ecological foundation is forming. As vegetation patterns shift and older herbivores decline, animals capable of moving efficiently and consuming large quantities of varied plant material enter the opening. The episode also affects smaller land animals. Increased moisture produces more ponds, wetlands, and vegetated ground, creating opportunities for insects, amphibians, and small reptiles. Early frogs become more visible in the fossil record. Turtles appear with increasingly recognizable shells, though their origins remain debated and their early relatives show a gradual assembly of protective anatomy. Cynodonts continue diversifying in the undergrowth, taking advantage of insects, seeds, and other small food sources. Wet conditions do not guarantee safety. Floods can destroy nests, drown burrows, and strip vegetation from riverbanks. Heavy sediment can bury aquatic habitats or fill lakes. Seasonal wetlands may expand rapidly and then disappear when rainfall weakens. Animals that depend on permanent water may become trapped when channels shift. The same climatic pulse that creates habitat in one basin erases it in another. In coastal seas, intensified weathering delivers nutrients from the continents. Surface productivity may rise, supporting plankton and the organisms that feed upon them. Yet when this organic matter sinks and decays, oxygen is consumed. Marine anoxia can spread through restricted basins, repeating a process already familiar from the early Triassic. Black shales and chemical indicators record episodes in which bottom waters become hostile to most animal life. Marine communities undergo significant turnover. Ammonoids diversify and disappear through rapid cycles. Conodont assemblages change. Reef systems begin expanding more confidently in parts of the Middle and Late Triassic. But the Carnian disturbance interrupts some of that progress. Corals, sponges, and microbial builders respond differently according to local temperature, sediment, and water chemistry. In shallow, clear water, reefs may flourish. Near river mouths overwhelmed by mud and nutrients, they decline. Marine reptiles continue evolving through the upheaval. Ichthyosaurs include increasingly specialized open-water swimmers, some reaching large body sizes. Sauropterygians divide into shoreline hunters, shell crushers, and more fully marine forms. The changing seas create new prey distributions and new corridors, but they also eliminate habitats. Once again, Evolutionary innovation unfolds within environmental instability rather than after it has ended. A lesser-known transformation may involve the spread of modern-style conifer forests and changes in resin-producing plants, which influence terrestrial food webs from the canopy to the soil. Plant resins trap insects and small organisms, later preserving them as amber, though rich Triassic amber deposits are far rarer than those of later periods. These small preservational windows hint at ecosystems that the large vertebrate fossil record barely captures: mites, flies, fungal spores, and fragments of forest life moving through the same climatic crisis as the giants. The Carnian pluvial episode therefore acts as both interruption and accelerator. It weakens communities adapted to long-standing aridity, intensifies erosion and marine oxygen stress, and drives extinction in several lineages. At the same time, it expands forests and wetlands in some regions, opens ecological space, and promotes the spread of groups that will become increasingly important. Its significance lies not in producing one immediate winner, but in changing the direction of the Triassic experiment. Before the rains, many ecosystems are still dominated by lineages rooted in the Paleozoic aftermath. Afterward, the balance begins shifting more visibly toward conifer-dominated landscapes. Increasingly diverse dinosaurs, pterosaurs, turtles, marine reptiles, and small cynodonts approaching mammalian anatomy. The world that emerges is richer, greener in places, and more recognizably Mesozoic, but it remains vulnerable. The rains recede, aridity returns to many interiors, rivers settle into new courses, and surviving lineages expand into territories vacated by those that failed. The Triassic has passed through another filter, and once again recovery has not restored what came before. It has cleared the ground for forms waiting nearby. Dinosaurs are now more widespread, but crocodile-line archosaurs still command many ecosystems. Forests have changed, but the supercontinent remains intact. The seas support increasingly elaborate food webs, but their chemistry can still turn hostile. The planet has learned to rebuild quickly, and it has also shown how quickly that rebuilding can be redirected. Beneath the apparent stability of the late Triassic, volcanic forces are gathering on a far greater scale, preparing to split Pangaea itself and bring another age of experimentation to a violent close. The forces gathering beneath the late Triassic world do not announce themselves with a single eruption. They begin as tension within the crust, where the supercontinent has grown too large to remain stable forever. Pangaea is already crossed by ancient sutures, weakened margins, and zones where the lithosphere is being stretched. Over immense spans of time, the interior begins to pull apart, valleys subside, faults open, lakes form within long rift basins. Magma rises through fractures that will eventually become the birthplace of the Atlantic Ocean. At first, these rifts are only narrow depressions running through what will become eastern North America, northwestern Africa, Europe, and parts of South America. Rivers drain into enclosed basins where layers of mud, sand, and organic matter accumulate. Seasonal lakes expand and contract under monsoonal climates. Dinosaur tracks cross their shores. Fish, insects, plants, small reptiles, and amphibians live around waters that seem ordinary within the rhythm of the late Triassic. Yet beneath them, the crust is thinning. Around 201 million years ago, that tension releases one of the largest volcanic episodes of the last several 100 million years. Magma erupts across the developing rift system in repeated pulses, producing the Central Atlantic Magmatic Province, often shortened to CAMP. Its lava flows and underground intrusions will eventually be found across several continents. separated only because the Atlantic later opens between them, reassembled on a map of Pangaea. The scattered rocks form the remains of a volcanic province extending across millions of square kilometers. The scale is difficult to imagine from the surviving outcrops. Lava does not necessarily cover the whole region in one continuous sheet, nor does volcanism occur as one uninterrupted outpouring. It arrives in pulses. Basalt floods across valleys, cools, and is later covered by sediment or another flow. Magma forces its way between older rock layers as sills and cuts through them as vertical dikes, where these intrusions heat sediments rich in organic carbon, carbonates, or evaporate minerals. They may release additional greenhouse gases and chemically reactive compounds. The eruption of basalt is only the visible part of the disturbance. Carbon dioxide enters the atmosphere from volcanic vents and from rocks altered by the invading magma. Sulfur gases can produce short-lived cooling and acid rain, while carbon dioxide drives longer-term warming. Mercury spreads through the atmosphere and settles into sediment, leaving another chemical trace of volcanic activity. The climate is pushed in opposite directions across different timescales. Brief volcanic winters may interrupt a broader greenhouse trend. This instability matters as much as the final temperature. Organisms can sometimes adapt to gradual warming or cooling, but rapid oscillation is harder to endure. A population adjusted to warm conditions may be struck by a short cooling interval. Vegetation damaged by acid rain may face drought when temperatures rise again. Marine ecosystems stressed by warming may also experience changes in runoff, nutrients, circulation, and oxygen. The crisis operates through repeated shocks rather than one clean mechanism. Carbon isotope records near the Triassic-Jurassic boundary show major disturbances consistent with large additions of carbon to the atmosphere-ocean system. Dating increasingly links several of these shifts with camp volcanic pulses, strengthening the case that volcanism drove the extinction. The exact sequence remains debated. Some eruptions may begin just before the most severe biological losses, while others continue afterward. Differences between rock sections, dating uncertainties, and gaps in preservation prevent a perfectly ordered global timeline. Even so, the broad relationship is difficult to dismiss. Volcanic activity begins as ecosystems are destabilized. Carbon cycle disruption intensifies. Extinction follows in the sea and on land. Additional eruptions then prolong the hostile interval. As during the Great Dying, the boundary itself is only one line within a longer environmental emergency. The oceans respond quickly to rising carbon dioxide. Surface waters warm, and their capacity to hold dissolved oxygen declines. Stronger stratification can prevent oxygen-rich surface water from mixing downward. Nutrients entering coastal seas stimulate productivity, but decomposition consumes oxygen at depth. Anoxic zones expand through vulnerable basins. Some waters may also become more acidic as carbon dioxide dissolves into the sea, making shell construction more difficult for sensitive organisms. Again, ocean acidification is unlikely to act uniformly across every marine environment. Local circulation, depth, productivity, and rock chemistry influence the response. Some organisms capable of regulating their internal chemistry may tolerate changing pH better than others. Heat and oxygen stress may prove more immediate in certain habitats. No single explanation fully accounts for the marine extinction, but the combination is devastating. Reef communities suffer heavily. Late Triassic reefs have regained much of the complexity lost after the Great Dying, with corals, sponges, algae, and other builders forming elaborate habitats. Their decline removes not only the reef constructors, but also the animals that feed, hide, and reproduce within the structure. Open water groups also experience major turnover. Conodonts disappear completely at the end of the period, ending a lineage that had survived for hundreds of millions of years. Ammonoids suffer severe losses, though a small number of lineages endure and diversify again in the Jurassic. On land, vegetation responds to heat, acid deposition, wildfire, and altered rainfall. Fossil pollen and spores record abrupt changes in plant communities. In some regions, forests decline and are replaced temporarily by pioneer vegetation better suited to disturbed ground. Fern spores may become more abundant, creating what is sometimes called a fern spike. Such patterns do not mean the entire world becomes one continuous fern-covered wasteland, but they indicate rapid recolonization after established plant communities are damaged. The loss of vegetation moves upward through terrestrial food webs. Herbivores face reduced or changing forage. Large specialists are especially vulnerable because they need substantial, predictable food. Predators then lose prey. River systems destabilize as plant cover thins, increasing erosion and sediment transport. Floodplains that once supported complex communities become physically and biologically unpredictable. Several of the Triassic's most successful vertebrate groups disappear. Phytosaurs vanish from the waterways. Etosaurs and many large Rauisuchian relatives are lost. Numerous archosauriform branches that once rivaled or exceeded dinosaurs in abundance do not cross into the Jurassic. Large dicynodonts disappear near the end of the period, closing one of the most enduring chapters of synapsid herbivore evolution. Many temnospondyl lineages decline, though some survive into the Jurassic and beyond. The pattern is not simply that dinosaurs endure while everything else dies. Some dinosaur groups also disappear, and survival varies by region and ecology. Small body size, broad diet, rapid growth, efficient movement, or wide geographic range may each offer advantages, but none provides universal protection. Dinosaurs that cross the boundary do so as survivors of a filter, not as predetermined heirs. Crocodile line archosaurs are similarly reduced rather than erased. Several smaller-bodied pseudosuchians survive and eventually give rise to the crocodilian lineage. Their persistence prevents the end-Triassic event from becoming a total replacement of one archosaur branch by another. Yet the enormous ecological variety of Triassic pseudosuchians is gone. The survivors occupy a much narrower range of forms than their predecessors. Small cynodonts also pass through the crisis. Their modest size, burrowing habits, flexible diets, and possibly insulating coverings may help them endure disturbed environments. Among them are early mammalia forms, animals near or within the mammalian lineage. They do not emerge from the extinction as dominant large animals. They remain small, often nocturnal, and ecologically inconspicuous. Their victory is continuation. Pterosaurs survive as well, retaining the skies while terrestrial communities are reorganized below. Marine reptiles cross the boundary unevenly. Some Triassic groups disappear, while others persist or are replaced by new Jurassic radiations. The oceans do not empty completely, but their ecological structure changes substantially. The extinction selectivity remains one of its central mysteries. Why do some small archosaurs survive while others with similar body sizes vanish? Why do certain ammonoid lineages cross the boundary when close relatives do not? Why do some plant communities recover rapidly while others undergo prolonged disruption? Fossil scarcity, local environmental differences, and chance all obscure the answer. Traits influence survival, but the crisis is too geographically uneven to produce one universal rule. Volcanism also interacts with the physical breakup of Pangaea. Rift basins alter drainage systems and create new lakes, coastlines, and migration barriers. As extension continues, seawater will eventually enter the widening gap. The opening Atlantic does not appear fully formed at the boundary, but the geological process that will divide the supercontinent is underway. The same internal heat contributing to extinction is also constructing the geography of the future. For the second time within the Triassic story, life faces a catastrophe driven by enormous volcanism and cascading climate stress. Yet the end-Permian and end-Triassic events are not identical. The Great Dying is more severe, striking a world still organized around Paleozoic ecosystems. The later extinction attacks a biosphere that has spent nearly 50 million years experimenting, diversifying, and building new forms. Its losses are profound, but more of the emerging Mesozoic structure survives. When the volcanic pulses ease and the climate begins another uneven stabilization, the land is missing many of its former rulers. The rivers no longer contain phytosaurs. The great predatory pseudoseuchians have largely vanished. Rhynchosaurs and dicynodonts no longer dominate the herbivore communities. Ecological space opens across Pangaea at precisely the moment when surviving dinosaurs are widespread enough to enter it. Their coming expansion will look sudden in the rocks, but it rests on everything that preceded it. Upright limbs refined during competition, respiratory systems shaped under heat, growth strategies tested through repeated crisis, and geographic ranges established across the connected supercontinent. The fire beneath Pangaea has not created dinosaurs, and it has not proven them superior. It has removed the crowded world that kept them from becoming dominant. As the Triassic closes, lava cools along the rifts that will become an ocean. Ash settles into lakes where footprints disappear beneath sediment. The survivors move through altered forests and newly emptied floodplains without knowing that a geological boundary has been crossed. Behind them lies the strangest recovery Earth has yet attempted. Ahead lies a Jurassic world built not merely by evolution, but by the repeated destruction of almost everything that once stood in its way. The Jurassic world does not rise from a clean beginning. It inherits a planet already transformed by 50 million years of repeated catastrophe, migration, anatomical experimentation, and ecological replacement. When the end-Triassic extinction removes many of the dominant animals of Pangaea, the survivors step into landscapes whose foundations were laid long before the first dinosaur became large. Rivers, forests, coastlines, and food webs have all been rebuilt from the remains of the Great Dying. The age that follows is therefore not a separate story. It is the delayed result of the Triassic struggle to make complex life possible again. Dinosaurs are among the most visible beneficiaries. Their competitors have been sharply reduced, especially the large crocodile-line archosaurs that once occupied many of the greatest predatory and herbivorous roles. Surviving theropods expand into newly available hunting niches. Sauropodomorphs increase in body size and geographic range, becoming the principal large herbivores in many environments. Ornithischians remain less conspicuous at first, but continue developing feeding structures and body plans that will later produce armored, horned, and duck-billed forms. Their expansion is rapid in geological terms, but it is not instantaneous. Early Jurassic ecosystems still contain many small reptiles, amphibians, cynodonts, pterosaurs, and surviving pseudoseuchians. Regional differences remain strong. A dinosaur group abundant in one basin may be rare in another. Climate, vegetation, and local geography continue shaping which lineages flourish. Even after their competitors vanish, dinosaurs must still adapt to a world changing beneath them. The breakup of Pangaea gradually intensifies. Rift valleys widen, volcanic highlands erode, new coastlines form as seawater enters the developing Atlantic basin. At first, the supercontinent remains largely connected, allowing animals and plants to disperse across broad territories. Over time, however, widening seas begin separating populations. Isolation encourages divergence. Lineages that once mixed freely evolve along increasingly independent paths. This geographical fragmentation will become one of the great engines of Jurassic and Cretaceous diversity. Dinosaurs separated on different landmasses develop distinctive bodies. Marine communities spread through new, shallow seas. Climate patterns change as coastlines multiply and continental interiors shrink. Pangaea's harsh central deserts do not disappear immediately, but the gradual division of the land allows oceanic moisture to penetrate farther inland. The Triassic has already prepared many organisms for this more varied geography. Efficient upright locomotion allows dinosaurs to travel across seasonal landscapes. Respiratory systems inherited from archosaur ancestors support sustained activity and, in some lineages, enormous size. Rapid growth enables individuals to pass quickly through vulnerable life stages. Egg-laying permits reproduction away from open water, while nesting behavior can be adjusted to different soils, climates, and vegetation. Sauropodomorphs push several of these traits toward extremes. Their necks lengthen, their bodies become heavier, and their limbs transform into weight-bearing columns. Large digestive systems process vast quantities of plants that offer limited nutrition. Air-filled spaces lighten the vertebrae and may connect to a respiratory system capable of ventilating an enormous body. The first true sauropods appear near the Triassic-Jurassic transition, but their later success depends on anatomical changes tested through earlier, smaller forms. Theropods follow another path, their lightweight skeletons, grasping forelimbs, sharp teeth, and powerful hind limbs support active predation. Some grow larger after the extinction, filling roles left by vanished Rauisuchians. Others remain small and agile, pursuing insects, reptiles, and early mammals. Over time, feathers or feather-like coverings become increasingly important within parts of the lineage, first for insulation, display, or sensory purposes, and eventually as essential components of flight in birds. The origin of feathers reaches deeper than the Jurassic giants that later dominate popular imagination. Their precise beginnings remain debated, especially because soft coverings preserve only under exceptional conditions. Yet the broader archosaur story suggests that body insulation, rapid growth, and active metabolism are linked parts of a long evolutionary transformation. Traits that begin as solutions to temperature, communication, or reproduction can later become the foundation of entirely new ways of life. Pterosaurs already occupy the air. They survive the end-Triassic crisis and diversify through the Jurassic, developing longer wings, lighter skulls, and a wide range of feeding strategies. Some catch fish from coastal waters, others pursue insects or small terrestrial prey. Their flight is not an extension of dinosaur flight, but an independent experiment built around a greatly elongated fourth finger. For more than 100 million years, they remain the dominant large-flying vertebrates. The sea continues its own unfinished revolution. Ichthyosaurs become increasingly specialized for fast open water pursuit, their bodies converging on the shapes of modern dolphins and tuna. Plesiosaurs emerge from sauropterygian ancestry with broad paddles and distinctive combinations of long necks or massive heads. Crocodile relatives begin entering marine environments, producing streamlined swimmers unlike their land-based ancestors. Ammonoids recover once again. continuing their repeated cycle of devastation and explosive diversification. Reefs return more fully as corals, sponges, algae, and other organisms construct complex marine habitats. The recovery is not a restoration of Permian reefs. Different builders, predators, and shellfish now dominate. The sea has crossed from a Paleozoic ecological order into a recognizably Mesozoic one. Bivalves are increasingly prominent. Mobile predators become more effective. Shells thicken, burrowing deepens, and prey animals develop new defenses. This growing intensity of predation is sometimes described as part of the Mesozoic marine revolution, though its strongest phases come later. Its roots lie in the Triassic, when shell-crushing reptiles, fast fish, ammonoids, and new benthic communities first began rebuilding complex interactions after the Great Dying. The revolution is not a single event. It is a prolonged escalation in which predators improve, prey respond, and entire ecosystems become more active. On land, mammals remain small. Their ancestors have survived 2 mass extinctions without becoming dominant, and their bodies continue changing in quieter ways. The jaw joint becomes more specialized. Bones once involved in feeding become part of the middle ear, improving hearing. Teeth fit together with increasing precision. Many early mammals or mammalia forms are insectivorous, nocturnal, and adapted to sheltered environments. Their small size is often portrayed as evidence of dinosaurian suppression, but it is also a successful specialization. Small mammals can hide in burrows, forage at night, reproduce relatively quickly, and exploit food unavailable to giant reptiles. They occupy a world beneath the feet of dinosaurs, developing sensory and physiological traits that will matter long after the Mesozoic ends. Their survival strategy is not immediate conquest, but persistence across deep time. Temnospondyl amphibians also cross into the Jurassic, though their former diversity continues declining. Some remain large aquatic predators. Others occupy specialized freshwater habitats. Crocodilian relatives survive in more limited forms than their Triassic ancestors but gradually radiate again. Turtles expand across terrestrial freshwater and marine environments. Each surviving lineage carries only a fraction of its Triassic variety, yet that fraction is enough to continue the experiment. Many of the most distinctive Triassic animals leave no descendants. No phytosaur waits beneath a modern river surface. No etosaur roots through forest soil behind a shield of interlocking armor. No rhynchosaur crushes vegetation with its grooved tooth plates. Tanistropheus, the giant dicynodonts, the rauisuchians, and most marine reptile experiments disappear entirely. Their absence creates the misleading impression that they were evolutionary mistakes. They were nothing of the kind. A lineage that persists for millions of years across several continents has succeeded within the only world available to it. Extinction does not judge quality. It records whether a body happened to meet the conditions of a particular crisis. Some highly specialized animals vanish when their habitat changes. Some flexible generalists survive. Others continue because a small population occupies the right refuge at the right moment. The Triassic teaches that evolutionary dominance is temporary. Lystrosaurus becomes almost synonymous with the earliest recovery, then disappears. Rhynchosaurs become major herbivores, then vanish. Pseudosuchians diversify into runners, tanks, ambush predators, and towering hunters, only to lose most of that variety at the period's end. Dinosaurs begin as minor participants and inherit the world after circumstances change. Their rise is not the inevitable conclusion of progress. It is the outcome of survival, opportunity, and contingency. The period also reveals that recovery has no single speed. Some river ecosystems return within a few million years. Microbial mounds provide marine shelter almost immediately by geological standards. Complex predators appear surprisingly early in certain seas. Elsewhere, oxygen stress, acidity, heat, and unstable carbon cycles delay recovery for far longer. A planet can contain thriving oases and devastated regions at the same time. Even the word recovery becomes uncertain. The Permian world never comes back. Its forests, reefs, and dominant animal communities are replaced rather than repaired. The biosphere regains complexity, but that complexity is built from different lineages performing familiar ecological roles in new ways. Herbivores return, but they are not the same herbivores. Reefs rise, but they are constructed by different organisms. Large predators resume control of food webs, but their ancestry and anatomy have changed. This is the deeper meaning of the Triassic rebirth. Life does not reverse extinction. It grows around the absence. Each vanished lineage leaves a space that another organism may enter, reshape, or ignore. Over millions of years, those spaces become a new world whose inhabitants cannot remember the disaster that made their existence possible. The last Triassic lava cools along the rift valleys of Pangaea. Rain falls on black basalt and carries minerals into rivers. Ferns and other pioneer plants spread across disturbed ground. Small animals emerge from shelter. Dinosaurs move through forests where larger competitors no longer wait. Above them, pterosaurs cross the open air, and beyond the coastline, marine reptiles follow prey through warming seas. Nothing in that landscape announces that the long emergency has ended. Climate still fluctuates, volcanoes still erupt, species continue disappearing. The planet has not become safe. It has simply become capable of supporting complexity again. Far below the soil, the bones of earlier worlds are already turning to stone. Lystrosaurus lies within ancient floodplain sediment. Ammonoid shells rest in marine layers folded by future mountains. Footprints harden beside vanished lakes. Mercury, carbon, sulfur, and iron remain locked in mineral records, preserving disasters long after every living witness is gone. Hundreds of millions of years later, those traces allow the story to be approached but never fully recovered. The evidence remains incomplete. Every fossil bed is a surviving page from a book mostly destroyed, and every new discovery changes the shape of what is missing. The Triassic continues to appear stranger as more of it becomes visible. Its landscapes belong to no modern world. Continents are joined in unfamiliar positions. Rivers cross regions that will become oceans. Animals combine traits that later evolution will separate into forms now considered ordinary. The period feels experimental because the future has not yet narrowed the possibilities. And perhaps that is the final image worth holding, not dinosaurs marching inevitably toward an age of giants, but a damaged planet filled with uncertain beginnings. A shell opening in oxygenated water, a small archosaur crossing wet mud, a dicynodont guarding the energy contained within a fragile egg. Vegetation holding to the edge of a river while heat shimmers across the empty land. From such small acts of continuation, entire eras are built. The Great Dying removes nearly everything familiar, but it does not remove life's capacity to improvise. The Triassic turns that capacity into landscapes, bodies, migrations, and food webs. It is a world assembled from survivors, shaped by disasters, and passed onward unfinished. The rivers quiet beneath the evening sky. Long shadows settle across conifer stands and open floodplains. Somewhere in the distance, an animal moves between the trees, too small and ordinary to reveal the future carried within its bones. The ground beneath it holds the memory of fire. The world ahead remains unknown, and for the moment, after millions of years balanced between collapse and recovery, the Earth continues breathing,